Các bạn tham cái trend đó mang cổ tôi bên nhỉ tức là bên đâu là vào it's about time. Good morning, everyone. Today, our first speaker is Andy from National Chongqing University. Joined this tour, and he much skill from Rutgers University, and was one of our latest research that had this skill of academic field theory. And so today we were in this morning we were about some development field theory and idea. And because of time, we would only talk about some extension or theory. And in the morning, we have a second talk, and we want to do more practical talk that we would show demonstrate the researchers program to everyone. And I say, student, you your data and have a partner and join us, and you will share this code. Okay. And that's a welcome. Thanks. So I am Lee from National University. And so today I'm going to introduce you this dynamic theory, where I have hearing this several times in the previous. So yes, so in this talk I'm going to introduce the theory before. And although I didn't involve in theory beyond and but I still think it's very important to introduce how So this is the outline of today's talk. I will first introduce you about correlated systems and correlated material, and some concept about quantum embedding, which is the basis of quantum mechanics. And then I will introduce you about field theory, and then we will go into about the EMFT formalism and why EMFT will become effectively when the condition is large. And then we will discuss, how we can solve the EMFT self. Then I will doing some implementation of the EMFT for both model and materials, and also doing some way that we go beyond EMFT describe low-dimensional systems. And then I will give you some summary. Okay, so let's start from the strongly correlated material. So strongly correlated material experimental atoms, and also the actinide and actinides atoms. And so the trend is like this. So if we go from 5D atoms to 3D atoms, we will increase the normalization of these electrons, and the function also atoms. And if we go to 5 and 4D atoms, we will also increase the normalization. General trend is like we increase from 5 to increase the normalization, and then over that we stronger normalization of the electron. So this normalization of the wave function can lead to smaller topping integrals between the ions inside the electron. This wave function will be sitting on the side ion and another side electron. So if the wave function is localized, then the overlap of the wave function will be very small. So we will have a very smaller topping integral. And also, if you look at the cooling reaction, total cooling reaction, hydrogen sits on the same. Then, if the wave function is localized, is strong, then we will have a stronger cooling interaction. So, in these correlated materials, generally the cooling interaction is about the scale. Therefore, Bayesian theory breaks down into region. Then give a high reliable result of strong materials. So in this correlating materials, there are two features that is quite prominent. For example, the atomic characters, as well as the heavy particle system. So here I take an example from Professor the spectrum, a series of transition metal oxides with the E1 configuration. And so radium is on the 5D S of the transition metal. So we can see that this wave function is more extent. So the cooling interaction is in this radium oxide is expected to be smaller than the kinetic value. So in this case, the wave function of nearest neighbor with each other. So the itinerant temperature works quite well for this material, and the mean field type of correlation from activity fits quite well with this autoimmune spectrum. But as we move from 5D energy to magnetic process, we can start to see that the RS automation spectrum starts to deviate from here. We can see that the peak start to emerge at these 1.5 dimensional volts. This peak can be attributed to atomic multiplex variation, where the nearest neighbor has P1, one dimensional, and fluctuate to another. So this chart excitation, the INP fluctuation, which we usually call as lower upper band. And then at the same time, coherent peaks start to show up around 30 level, and the bandwidth is much smaller than the DMP bandwidth shown here. So in this example, you can see that our feature is transition. And especially in outside, where the system becomes later, and there will be no negative state at the early level, only this show up, and this corresponds to the whole modulator, and can be used as and very small. So we can also see this coming feature in temporary compounds. We can see the sharp fluctuation for these sectors. And besides these atomic features, it also shows these sharp heavy quantum particle peak at Fermi level, which is known as screening ring electron. So yeah, we see here the feature and these things quite important roles. And so here physics, atomic physics quite important. So from Professor Yang and Dao's talk, we also know heroes, we also use we all know examples of the Fuji shell. So the spin charge and wire interplay of this freedom can be any interesting physics. For example, complicated of the engineer acids and without potassium, there will be a lot of different kind of magnetic transition, and also there will be a sort of activity which is spin fluctuations. And in our series, we also see a lot of examples of especially in this region where now we look at the chart spin and carrying fluctuation people running. So spin any interesting. So the problem for theory is that generally DFT and linear theory cannot capture this kind of so very badly approaches the develop and also utilize explore or understand the material. Yeah, so now we can describe the challenge in the main problem, which is typically topic of this electron prediction. So here we take the Hotta model as an example, where the Huffington from side I to some side J, the linears, and the is the challenge of the problem. So the most easier way to attack this is to the particle transformation, cause this into a simple term has some effective potential done by the average density. So after doing this, we can transform this problem to a single particle problem. And if we analyze this single particle problem, we can get some particles, some energy, single particle energy levels. Then the strong state is particle state when we figure out the electron up to the certain level. So the work is the vacuum state, and then we start to get the electrons until the certain level. But this particle population is generally not very accurate. So finitely, so one can notice that when U becomes large, then this is what this BX inside. So one way to prove this from chemistry perspective is that one can create some excited state configuration. For example, we can create a here, some state above. And this is described by this whole expectation where we want state. And we can also prove it by describing P bubble. So we create a state. Okay. So this kind of still or fraction is small. When we start to break up the fraction, we will see a lot more state and link to exponentially growing space. And it is very hard to solve using our and so this particular challenge in computation of physics, which has been so here we will go from another perspective, which is different from the metric product state. So since we know that in correlated materials, the local correlation is quite prominent and essential. So here is maybe we can pick an atom, then we can solve the and then we can treat the environment atoms, the rest of the atoms as our environment. Then we can transform this interactive lattice problem into a quantitative environment where this and there's an atom, and then there's local functions. So there has to be some self-consistency that we can determine the environment that can represent the original lattice pattern. Based on this idea, there are many approaches that have been developed. Which is so recently we can transmission and also also some
chemistry, which energy delivery and energy transmission. So today we will look at this probably one of the most popular approach. So yeah, dynamic homogeneous theory and approach and totally based on important findings from Wexler and they found that when the dimensionals become large, then the self-energy originally about two different sides of the vertex will collapse to the vertex, then it only depends on one side. So then the self-energy will come to a local self-energy, and a local self-energy becomes can see that EMFP is exactly the direction, and we will complete this in our picture. So, because the gel energy becomes local, then we will lose the momentum. EMFP energy so, by this assumption of larger dimensionality, one can map exactly this vector length problem to a purity problem for dimensional properties. And we also see and finally the cell consistency condition requires local consumption of this has to be the same as the pure consumption on this head. Say it is 0.5 approximation. We also have pressure so now we can go them and try to understand why theory becomes that, but goes to so before going into the dynamic theory, we will first review the so in the classical model, that is describing the direction of the speed of the nearest neighbor, and we have this local field, electric field, and this is the original and of the IC model. And in this linear approach, we can also map this IC model into some kind of impure model with the spin coupled with environment. So we have local spin coupled with effective. And the effective environment is of magnetic field edge and times which is the lattice coordination, and here it is 4. Each element of the 4 networks, so we is and then times J, which is actually the speed and magnetic moment M. And the local observable here is the magnetic, which is one can compute average of the speed, which will give us this interval. You can see that it consists between the consistency condition selectively. So this is the classical field theory, and can describe transition from very negative to very negative, where the polarization is zero as a term, and become sunlight when the speed starts to in a very fixed. And there's also a transition if one switch the magnetic field. And so in one computer station, see that this medium theory has this powerful exposure of the CPM, which are beta 1/2 for one magnetic field. The power is 1 over delta, where the delta is 3. So this is a critical component that. And so now we can consider the structure. So use this Hotta model as an example. We have the nearest neighbor Hotta and the blue structure. This is our signal and then our effective Hamiltonian is the Henderson model that is described on this presentation. About the delta coupled to the atom. C. So, which is connected to the picture, which is so now the local observable of the European functions. Then the second consistent condition is our impurity function has to be the same as the function. So is the sets of very close structure between classical impurity model and impurity. And the main difference is that here the environment field is not static, and it's and which is function. So now we will want to see why we have information of the speed. So this is in the so we but we will see what is the dimensional, how is the dimensional physical model. So here we have one model. So dimension is 1. And B is the dimension. Here we have this size. And also we see that is corresponding density. And from 2 dimension, we can see every force. Force is 4 dimension, and here is the metric showing the force here. And this is on dimension 3. And we see that it has 6 the very element which is 5, 6. It's the and close to 8. We see the 4 is 8, and now that imaginary relative growth, the density of state kind of getting closer to a Gaussian type. So you can see as the dimensionality goes to infinity, density of state. Same time, the bandwidth will as so we have to normalize some of the same time so that we will get finite increase in density. So this is the just for how dimensionality to using hyperfluid methods. And there's also another artificial analysis that to show impurity effect and structure. So it has this fractal-like structure where it happens and we calculate this density of state for this kind of lattice as we go to you can see density of states some certain circle type. So this will be useful at so now we can start to see how the density matrix or the green function scale as we increase the dimension. So we can see the steady limit of the green function comes to our density matrix, and here it is a green function of Cj, so Cj, delta Cj. So it describes the transition of the atom from J, Cj to I. So we can view this view this type of transition as a probability, and we expect the square of it will 1/2. There's a lot of neighboring atoms, the dimensionality grows. So we said the probability of the Hopkin scale is 1/2. And from here, we can start that the green function will be scaling over 1/2 square. We consider the nearest neighbor Hopkin of the green function. But for general Hopkin, you will close like this 1/2 and J is absolute sign. This absolute sign we are counting the numerical distance between J. So this red line is the Euclidean distance between I and psi J. And the Manhattan distance is that we are imaginary, we are working pattern of another street plots. So we are counting how many edges we have to test J. So here the Manhattan distance from I to J is 1, 2, 3, 4, 5, 6, 7. So count on the grid test, it is also 1. So here the I absolute value of I minus J is this Manhattan distance. Now we know how the green function scales the dimension. And we also still need to know Hopkin scale as the dimension here. And we want our density of state to be finite, which also means our energy has to be finite as t equals to infinity. So here we see that the green function scale is we sum over the kinetic energy, we fix one site, and sum over the neighboring sites. So this summation is from the order of G over the neighboring energy. So from here we can see that T has to be scaled as 1/5. And if we consider general Hopkin, then we also scale as the order of 1 mechanical distance between J divided by 2. So this will be useful later So now we start to take functional analytical approach. So we have our upper model, And we can write down the condition function where we have this function integral over the, so we have this integral, this number Ci equals Cj, and times this potential to the minus S, where S is the action. So the action is like this. We have the integral on the imaginary type from 0 to beta, where beta is our inverse of the temperature, 1 over kT. And then we will have this time derivative difference plus our Hamiltonian. So we can see now here it is our Hamiltonian. So this is the action of the model. So now we can separate our action into two parts because we want to have our lattice problem to impurity problem. So we will write down the action of this atom here, which is just a chemical potential plus the interaction sitting on this impurity atom. And we have this hybridization that describes the hybridization between the atom at 0 and between the atoms surrounding them. So this is the hybridization term. And S is parenthesis 0 is the so-called cavity action, which is representing the rest of the atom. And we can see that there is some track out of this original action. So we want to integrate out the rest of the atoms, so then it can become function. Yeah, so our next step is that we will treat this delta S as our function. And then we want to integrate all these Ci, which represent the rest of the atoms. So this can be used by computer extension into this type of the form, where we define this variable that is hopping from purity 0 to the other atoms type, and times the purity annihilation operator C. And here we are expanding our computation with theories. So here we are at the order of n. We have n particle Green's function times this power of n. And now we can start to count the power of each computation series. And we can realize that only the lowest order will survive in this expansion. In this expansion, and so that is how S20 or dimensional goes to infinity. So here we can look at the lowest order of this expansion, which involve I and J, I1 and J. So n is 1. And then the Green's function is a single particle Green's function, capital Green's function, which is I and J. How? And we can count the dimension of each term, where this dimension of I and J will give us a dimensional square and over 8 atoms, which goes as D. So dimension is and T, we know our previous results. We know its scale as 1 over D. Consider the nearest neighbor. This Manhattan distance is just 1. So it goes as B squared, and so it's 1 square root of B squared. And if we see the Green's function term, we see the Manhattan distance is 2, back here, 1, 2. So the scaling with the dimension is 1 over square root of B squared, and we can check that this gives us an order of 1. So this is the only relevant And if we go to the next order, we can see that it scale as 1 over d. So we dice out as our dimensional goes to. So we can now see that this first order term is just a hybridization function surrounding this atom 0. So this shows that yeah, this type of mapping from lattice to impurity into its effective impurity and component is exactly the dimension. Only the lowest order terms survive and can be replaced by the function function and our original action impurity model. So this is the first step. We show that the action is exact transition. We can do the same thing also for our self-energy, which is shown first by Mozart and. So here we have the second order self-energy involving 2 different sites scattering of you can see it as a scattering. And this line corresponds to our Green's function, which is our indicator, and we know that the scale as 1 over square root of d. So if we want to compute the self-energy with some of one of the vertices, and then we also have to times the power of each Green's function, and we see that it is square root of 2. So we can see that when d goes to infinity, only the local terms survive. So when the dimension is large above to infinity, our self-energy will just a local vertex where I has to be equals to j, and our self-energy becomes a local self-energy, and we don't have this momentum dependent on the self-energy. And because this mapping to an impurity Green's function is exact, and we also know the self-energy is local as the infinity goes to the dimension goes to infinity. So it is natural that we can expect when we find the exact solution, the local Green's function will be equal to the impurity Green's function. So this is the self-consistency condition. So the conclusion is that the mapping into a impurity model is exactly in infinite dimension and a function when the dimensional merit is large. And the self-energy is local for large dimension, or therefore we can obtain from here that DMFT is exact quantum theory in infinite dimension. Yeah, so this summarizes the DMFT formalism, and once we get the Green's function and the self-energy, we can derive the free energy of this system using the back catalog technique, the energy functional. And here we have this impurity free energy that contains this phi functional that we know is the Latinger-Watt functional. And if we can do this, if we want to get a self-energy of this approximation, we can do this variation of this functional with respect to our big function because self-energy. So this is the Latinger-Watt functional if we spend and this derivative just means that we have a line. This gives us the metric term, and the line this will give us second order integration. And in DMFT theory, we assume that our Green's function is local. Therefore, this Latinger-Watt functional is self-energy. This will only involve the local function, and the dimensional goes to infinity. So here we can see that this DMFT method can be formulated using the band catalog functional as well as the Latinger-Watt functional. Therefore, suggests that it is conserving approximation that satisfies the several conservation goals. And we can choose the level of our approximation. So if we compare our linear one to the second order, then we are solving the DMFT equation using the so-called iterative theory. And if we can solve this series of self-energy using the NRG Hotta approach, then it corresponds to the sum of all the self-energy. Therefore, we can get the very accurate local physics using this numerical set. So, yeah, so this summarizes the DMFT formalism. And now we start to see how we can solve the DMFT equations. Yeah, so as I have discussed, we have this Hotta model, and we have this into a set of self-consistent equations of the impurity model. So the way of solving this, one way to solving this is like this. We will start from initial class of the function, transformed into power frequency. Then we have this effective action. Then we can solve this action using any type of the technique we want to get the Green's function. So we can use NRG or multi-color methods to compute the Green's function. And once we have the impurity Green's function, we also know the fair function, how does it look like. Then we can extract the self-energy. And then we can use this self-consistency condition where we compute the local Green's function by summing over the lattice Green's function with the self-energy from here. This gives us a local Green's function. And with the local Green's function, we can invert this to get a new hybridization function. Then we can see if the initial and the new hybridization function is converged. And if not, then if it's converged, then we can stop because we find the solution. But if it is not converged, then we will go back to this loop, and then we will loop this circle until our hybridization converges with some desired activity. So this is quite simple. With some impurity, so you can write with just a few lines of code. But the crucial part of this is how can we solve this impurity model. This is a very hard problem, and we have discussed several speakers. So yeah, here one of the very popular ways to use this so-called continuous time quantum model, which scale quite nicely with the number of the orbitals. So for example, if you want 7 orbitals for the next systems, quantum model can do it quite easily to some, as long as the temperature is not very high and spin orbit coupling is not too strong. And we also have the numerical renormalization of this impurity model that has been discussed by previous speakers. And we can also solve it using density matrix renormalization, which is also very common research. And another easy way is to solve it using exact hybridization by discretize the mass hybridization mass to some small size of the orbitals. And we can also solve it using perturbation theory that I have discussed. The second order perturbation corresponds to this perturbation theory. We can also solve it using strong coupling computation approach, such as the state particle and Gaussian oscillation. So there are many ways to do this. So and different way has their own advantage. And if you are interested in several reference here, then
before you talk about a potential function, but we need to evaluate. We will need to calculate the potential function by before.
This one?
No. There's a
Oh, one function.
Yeah. Do we need
that? Yeah, so basically these are self-energy, and the simplest way is we can truncate it just here.
Okay.
So this is half tree and come over to
I mean, when we do iteration to get the same, we really calculate this.
Yeah. So usually we use numerical computing, checks, assumption, and some of the system for the so we start each changes.
Technical question. So it's also difficult to compute correlation function.
Yeah, correlation function. I think Professor found out recently as a way to do this for function. Continuous time how long they have a way. Instead diagonalization, we also do it now using the length source. I'm not sure about DMRG. Probably I haven't seen the application for this yet, but maybe we could do that.
How will it do real time?
So the most popular one is to follow the diagram of the real time. Yes. Not sure. I seem to see the manual. I think that is called diagrammatic. I'm not sure. Yeah, maybe, I think that's it.
Sorry, for the actual question. So, regarding to figure, sigma, self-energy, there are two different self-energy, right? One impurity part, sigma, omega. If I use NRG, then I can get a sigma omega. But what about the local self-energy from the original, say, lattice problem?
Oh,
so then I use NRG to get a sigma, and I should plug this in back to the local.
Yes. Yeah, because we expect they will be the same from the solution.
Okay.
So we can do this.
However, if I do so, do I really need to kind of diagrammatic expansion from this functional that
no. So if we do NRG or hello, it's our Z diagonalization going to be any diagrammatic use, but we want to make sure it's not the same. Okay, so we can classify them as two different ways to solve it. One is some kind of a theory based, so we are solving the actions, and the other is so-called Hamiltonian based, where because the method cannot solve the system in a continuous way, so we have to discretize the best into several orbitals. Then this finite size of the impurity model, we can solve it using tensor network technique or Z diagonalization technique. These are all quite promising. So yeah, in our tutorial in this afternoon, we will have a simple code to solve this using stack diagonalization. Yeah, so we will discuss this later. Yeah, so there's only a slight modification if you want to solve it using this three time space. Because we know the hybridization is this V, which describes the hybridization between the impurity and the orbitals. And EL is the energy levels on each orbitals. So, and our Hamiltonian now becomes discrete Hamiltonian, and we solve using the diagonalization, the Green's function, exactly using this method implementation. So there's only a slight modification. Our initial will be V and also L because it is organization. So we can give it some random guess of a organization, and then we solve for Green's function and using this energy and but here once we get a new hybridization function, we have to fit this new V and epsilon L in order to get a new parameters for the hybridization and energy level. So, and if it is not converged, then we can iterate it to the hybridization function converge, or which means that we converges. Yeah, so this is the only modification we will solve it. And for the special case, one can show that this self-consistency condition will become just this simple equation. So hybridization will be just the t square of the triangle. So once we get the triangle, we just here, you can just put it here. Hybridization. So when you consider the mathematics, we have this kind of property. So it makes the implementation simpler. So here we will use this. Yeah, so now after we have the conversion Green's function and self-energy, we can get a special function which is defined from the function. We can extract the quasi-particle parameters, which is the quasi-particle weight, and also the scattering rate is the imaginary part of the self-energy at zero momentum, and this is the usual way on the quasi-particle weight from the self-energy. And we have the free energy, total energy, so we can compute the thermodynamic properties as well as the forces or thermal properties. And susceptibility, we can also get it. So the first thing we do is compute the local susceptibility or local to particle Green's functions. And now this is just a bare bubble, and then we can subtract these filters to get a vertex. And once we get a vertex, we can compute the susceptibility using this beta equation, which just sums up the bare bubble and the bubble with vertex protection and sums it out to infinity. So we can compute the susceptibility with this. We can also formulate it with Volta symmetry, so with superconductivity, using Mandel's formalism, we can also start. Okay, so yeah, this is how we get this observables.
We do a question.
Yes, we can observe also severe averages. Also, calculating some correction of it. We can respond the corrections. Also, it seems that I'm not sure. Yeah, so these are the observed poles. Okay, now we have some time. We can look at some application of DMFT to some systems. So the first very early example discussed by Professor McDonald on this Hotta model. Yeah, so we know that when we turn on the Coulomb interaction, double occupied state will cost a lot of energy. So the electron, if we have field, the electron cannot hop around because if we hop to the other side, we will have this very costly for the energy. So when the U is large, the electron will be localized on the sides and become a insulator. So we know there's a transition from the metal to the insulator as we do interaction. So if we compute the density of state of this from small u to large u, we will see that it's the small u we still have some kind of feature, but lower and upper band emerges. And as we keep increasing, we can bands around the Fermi surface start to get normalized and become narrow as we turn on the Coulomb interaction. And near the one transition, the citation will be very narrow, so the effective mass is very large. And then as we go to the insulating phase, this positive heat disappears. And this phase diagram very well with this vanadium oxide, where we turn on the pressure, which means that we are kind of decreasing the Coulomb interaction because pressure will increase the structure. So when we turn on pressure, we are kind of increasing. That's the first order metal insulator transition, just like this here. And yeah, so in our tutorial, in this session, we will compute some metal and insulator solution using DMFT Z diagonalization. We will see the metal and insulator, and we can also observe the cell energy shows permeative behavior, where there is depends on square root with the frequency. And in the insulator, the cell energy diverges, so opens up a gap. Gap is about 4 P, which is the order of U. This is our tutorial. So, so if you want to measure this vanadium oxide more carefully for its transport, they indeed observe this type of curves as we increase the conductivity. As we change the temperature and the pressure, pressure corresponds to the U temperature, and the first order transition, and similar to DMFT. And one can extract also the critical component from this transport data. And we can see that as we go from this going to the free component, this curve can be filled by the component delta equals to 3, and close to the critical point it goes to equals to 5, which they say close to the 3 PIC as exponent. Similarly, for here, for the conductivity, this one is the switching pressure, this one is switching temperature. There are some also going to compute tests. Yeah, so some people compute the direction beyond DMFT and also suggest a 3D system as 3D as yeah, but if we want to just use the DMFT, we double occupancy, and we can also see it's expecting some DMFT feature. One can extract the exponent is just a linear exponent, which is the same as one observed in the experiment. So this is finalized and kind of explain this outside. But recently, we can also apply this DMFT approach on realistic materials by combining with the DFT. And the idea is that we can construct from DFT, we can get a band structure. Then we can construct the pipeline model by fitting some kinds of basis set. And then this we can project this low energy. Here we have 3 bands for these assets. And so we have a 3-orbital model. And then we have to solve this model using, for example, the energy can be as a level. And then from here, we can compute the charge density, which can be feedback to the DFT that is living within this changeable potential potential. Then we can move this circle until this charge density converge. And we can get this standard solution. So what this is an example that we can apply to this shorter where the dots are the data and the gray curves are DFT fitting to the type ID. And we can see the bandwidth extracted from DFT is quite large compared to the office data. But if one compute this spectra using DFT, which are the black dots here, here are the charged particle band extracted from EMFT. And we can see the bandwidth now is quite close to office data, where the bandwidth is really normalized by this quasi-particle weight, which is about 0.3. And so the effective mass is about times larger than the mass by the DFT. So one can compare the spectrum with study with APES, and we see this quite good agreement. And another very important example is to apply to iron-based superconductor to study its normal state and superconductivity property. So they calculate this effective mass for a lot of different iron-based superconductor. And the star here are the experimentally extracted effective mass. The curves here are the EMFT estimation, and you can see the largest effective mass are all quite close in the observation for all these selective iron-based compounds. And one can also compare the magnetic moment with the neutron scattering data, which are discussed here. You can also see the circle from EMFT and star are experiment. And these are the calculations that the EMFT used. Vector, and the class are the neutron scattering. And moreover, they compute the leading order of this pairing symmetry using EMFT vertices. Got this type of gas structure, which also due to experimental data start here on pockets, also systems. So yeah, so it seems that EMFT capture quite essential physics, quantum physics in this iron-based superconductor, and therefore we get a quite accurate effective mass, magnetic moment, magnetic structure, as well as the gap function for these iron-based structures. And recently, one can compute the spectra using the so-called frozen using parts of experiment and the recursive also shows quite good. So I have sometimes I will skip a figure that is described by Professor Hotta previously. So one can formulate EMFT this average contour. If once then we can assume the self-energy still be local. And then so we set an equation one can this possibility that steady state, and here is some indication to show the block and span the Hopper model, issue. Yeah, so I will discuss by briefly how we can go beyond DMFT. So as we know, DMFT ignore the spatial point fluctuation and also the critical point spatial point fluctuation. So one way and 2D Hopper model and provide a very good playground to benchmark this approach. So one way, straightforward way is that we enlarge our purity region to close more elements. So here for this Pinkerton, here is in 2001 from the Houston and they have a Pinkerton cluster which can describe the family of sites. And then also the anti-ferromagnetic overview. So they compute all the parameters they found with capture the main feature of it, but still there's a consistent and then we can also formulate this DMFT in the moment space, so we can separate our renewal zone by different patches, and then we can treat each momentum patch as a unity model, and then we solve it on these 8 edges in the momentum space. Then one can observe this set of the sugar gap by observing the density states. Also, set the sugar here, if one go from here to here, we can see the sugar gap here, the spectral function. There's some disturbation that is recently, there's also very important work from Jami and Zen, also from some Mayer. They calculate DMFT or DMRG, carefully compare DMRG and Monte-Carlo on the DMFT. They can observe kind of strong interline between the charge correlation, spin correlation, and pairing correlation. Interesting region. So these are the cluster DMFT, but cluster DMFT still has some shortcomings. One is the Hopper model where there's no transition and finite temperature. So, but cluster DMFT still has a transition to magnetic phase. So another way to improve this shortcoming is to improve the diagrammatic correction from DMFT. So here, one way of this is to add the dipole correction to the self-energy using the standard information theory with view. And one of the diagrammatic approach beyond DMFT is that we can replace this Coulomb view with the DMFT vertices, which contains important local correlation effects. And this approach, this correction to the self-energy is called the dynamical vertex approximation. And there are also other different types of the diagrammatic way to improve DMFT for dual boson and fermion. Also combined next diagram is DMFT, which is summarized in the multiverse view paper. So one can observe the magnetic transition of this different method by checking the spin susceptibility with staggered moment I and static susceptibility at first Mark-Barra point from high temperature to low temperature. And this so the orange curve is the RPA mean field height showing divergence. Temperature and DMFT also diverge here. And the divergence of the susceptibility means that we are having stability towards the magnetic phase. And the black dots here are from diagrammatic color, which is we can say is short and close to that way stability. And we can see that computing this correction using vertex, there's a divergence of it. So that there's not diverging to the and it is very close to this and they also carefully comparing to some approach using only the bare indexes, and we can see some improvement of this benchmark from so this is the recent benchmark. That shows this. So I will now skip this and go to the summary. So here I show that UMFT is exactly dimension, but it is still quite applicable to finite dimensional system, where the local fluctuation is less prominent. So for the low dimensional system, there's the diagonal way, classical way, to capture the local fluctuations, which is quite promising. Also, EMFT framework is quite an interesting playground for me that it kind of combines different field of physics, field theory, there's network, and material science. And so it's quite interesting playground to explore physics, techniques, and applications. So the outlook, we still have to go full and mutual calculation. We still have the input interaction U and J. So one way is to go material simulation without parameters to combine with the. And also we have seen some benchmark of this diagonal and classical. But still we must not be trying to release it. Also, to do this material more efficient, pure solver and define configuration algorithm, which is called by so on. And also, we need to develop more efficient embedding algorithm because TMFT is still kind of expensive. So if there's a more efficient way, we can with small atoms. So here I would like to know that we apply vibrant community of the world, and especially if you want to manipulate a Green's function and do the convolution of Green's function, tricks and code will be a very good one because of the hollow implementation. And if you do want to start the materials, these are all very nice software, including this tutorial, which is developed by. And if you want to Librium, there's some library of this Librium that is developed by. And also for the student, I think there are many interesting opportunities for students because of these tools, which I learned in PhD. So we provide financial support based on the metro at each September and Living Germany. And they have a nice website, summarize a lot of material, teaching material for the past more than 10 years. And also there's this international summer school of computational quantum mechanics made each year in Canada. It is also a very nice opportunity. We are belong to okay. Also we have other kind of accessibility. So finally I want to say there's an translation in Japan, we will check this. And my student can has to go to the code here. So if you are interested, you can start to download the code and look at it using the spec. And with this, I would like to thank you for joining us.
So, your impurity, do you minimize your impurity basis?
Impurity basis.
You show that you can use. So you show that you can use real space and real space. Does any method would kind of minimize the orbitals for the.
Also, the orbital the energy level is how we change is the elements is a change. Something and similar.
Orbital impurity is always space.
Yes, it's linear.
Is it possible to update it? It will be useful.
Yeah, if you do something, for example, you will have a string action, which due to some other type of action, and the string action will change. Okay, so this is called it's anti-reality, or
So you show that we can compute this. So our other response for other kinds.
Yeah, so density doable to do that. So all kinds of response can be calculated with diamond.
It's integer word formalism. So that will be consistent with that integer word function. So everything is conserving.
Yes, in DMFT it is conserving, but if you do something else, diagonal correction, then it has been shown that there are some problems from this dynamic based approximation. So they have to kind of enforce it and do some additional parameters.
Technical problem. So in the geometry of the if you're correlated orbital, it's some correlated orbital. So you example, if you
Yes, for this we use EP model, or to treat for the uncorrelated one. It's not an offset of orbital. But we still have the so we will only treat the correlated problem as a pure model, and for the non-correlated one, we treat it as some uninteract orbital, but their effect will just be hybridized with this correlated set. So usually it's called the EP model. Oh, yeah. Right. Yes, yes. Oh, yeah. So here we they are tracking spans from the function. So the K, yeah. So the K, yeah, it's here. So the initial energy is local, but still it's here. So is yes, yeah.
basically in our combination of EFT and EFT. So interaction strength is estimated from EFT.
Yes, so usually we do delta in type of combination. Yeah, so which is we are focusing on some energy level of the model. Then we have to incorporate our US events.
That's I know in most cases you basically use the imagery time most of the time, but then you have to do with the initial complication.
Yes.
And then that's also
yes.
And that's why people start using this space network because it's going to real time.
Yes.
So is there like is there like a preference of people or just it's like what because I mean beauty solver algorithm is actively developed. You need a beauty solver to accurate. Other than that, what's the technical barrier for experts?
So I think the most preferable way now is still on the Monte Carlo because it scale quite nicely as the total population. So I think because on Monte Carlo, still using set analyzation, which is
Let's take a break and let's come back at 10:45. Thank you.
比较那个，你同样的约大学潮水的，可以看这个，上面看这个 data point， 搞不好可以得到一个你有 combination 这种。我觉得可以，因为这个是一个 u define 的问题，因为很多种不用产品会然后你这样 sample 都会有一些 error。
其实
你凯西有些 idea 它用。对啊，
我跟你们比较合作，
不要你们提到的是，因为你现在要做的，你没去看这样的那些谁法。
你要拿那个停车券吗？
Thank you. Okay. Well, you can hear me, right?
Hello. Oh. Hello.
Anyway, I can start from a short entertainment, which you don't have to listen to that much. But you can see this photo. I found out this photo quite recently. So you know who he is. Yeah. I like this photo. Okay. The photo is 2010 in the Great Wall of China. Okay, this is and now, yeah, you can see this guy who is going up. Who is it? So 5 minutes ago, he was down there. And then, next few minutes later, we got onto the top. And here, I don't know why Ian is there anymore. But do you remember what happened? This is the top of the wall.
Probably looking at the views.
Okay, and then, so, but now we see the sky with red. And people who know him can recognize who he is. But now is Lawrence Chen, who invented this DMPT. But this was 2010, so they were not working. And 2 years later, in this paper, he proposed the method called DMPT. And then another 2 years later, I met him in another conference in Beijing. And I was like, I listened to his talk, and he was explaining the DMPT in a different manner as I want to do today. But I was quite inspired by his talk and so I'm going to start from a short film, just repeating some of the things that had been already taught in this summer school, but it had related properties, and then just make a bit of exercise on ferroelectrics and go into the thing in place. But now I was just trying to make it less technical and to make it more like about the basic ideas and concepts and the structure of the method and see how it works and how it results. So go on. So let's first talk about the related properties. So far, I see that there's a state separation in this community as well, just like in Japan, that we have like, basically roughly 3 classes of people. Like one's going to study tensor networks, grow these wave functions. Okay. Another thing is that like DMPT, validating the physical quantities using wave functions, you can do many basic methods, which is strictly straight apart. And there's also a whole bunch of effective theory using our beliefs and
It's fine.
So, now that because previous we was talked that was something which was first introduced. Scotland try to push the direction of the being and B. But I think there's a kind of a bit of misunderstanding that even is not close to the transport network and these like the basic idea. So let's go ahead. So we focus on the method with wave function. So in these graphical methods, we want to solve the basic problem of this H5 and if you get a nice round state, you can evaluate all physical quantities by the updated wave function. And we can also construct the density operator. And once we get the density operator, we can evaluate the quantity now, the difficulty here is that always we have a moving up of the dimensional real estate of the so the maximum system size we can afford with this method straightforward so but we know right now already that we don't need that much numbers of states. We know that we only need a tiny subspace of the large subspace. They're the accurate wave function. That's why we can get okay, then let's go to the basic concept of label density habits. But if you have a round state, let's make the system divided into two parts, 8 and 8. And then we trace out the equilibrium. It's not going to make that we didn't make it. I don't think like in terms of the base name. And here, if you can write down the round state based on the basis name, which is the basis in A and B, we can make this coefficient in a way that it's a square matrix with the dimensions of the space of A and B. Now, this non-square matrix can always be made Schmidt-Dick in this way. There we find a transformation that converts the original basis of A and B by using this matrix U and B to those who are like alpha and beta. And once it is transformed, we can only find the connections, one-to-one connections between the different bases belonging to A and B. And then the numbers of this summation I is shrink to the one and lowest dimension of either of the kernel space of A and B. So it becomes much more simplified. So this Smith composition will be very useful for all different networks related to this local distribution. Now, one important quantity is the entanglement. Now, once we get the local matrix, the diagonal matrix, which is like this, then with these Schmidt values on the square, which we have just already derived in the previous slide, we can characterize the nature, quantum nature of the ground state using this distribution of lambda. So if lambda has a highly biased distribution like it, and only one value, which is finite alpha, we get an entanglement entropy 0. And this is a typical product state. Now, if you have a large spread distribution of this lambda square like this, you get an entanglement entropy of this distribution, which is large. So, but the absolute values of S not so much. The important thing is how they load up with the subsystem type. So this is a very famous result in the paper by they have calculated the entanglement entropy in a subsystem chain of XX, etc. And here you see that the entanglement entropy is sometimes like this flat, which is a product. Now, in the case of this like stable curve, we have a logarithmic growth of entanglement entropy source 65. And here, in this case, we call it the case that we can describe the ground state only in a tiny subspace of the whole group. In this case, we can effectively use the clear margin and tensor network very efficiently to describe in Google as well as the ground state. Okay, so we want to go to this direction. And now then there's another quantity which is more detailed. Previous environmental entropy has integrated this distribution to see how it's going to be distributed. But now we want to see each of these values, how they look like, therefore we have a spectrum. So suppose that this rho A, again, we just do the Schmidt decomposition and diagonalize this density matrix. And then you can see that this rho A in the operator form could be given in this form of the exponential minus HA over CA. This looks like a Boltzmann weight. You are familiar with this shape, right? And then you can see that this HA is given in a diagonal form using the bases that were used to diagonalize this. And the Schmidt values were created in this way to the entanglement spectrum. And this is important because this entanglement spectrum is considered to be the fingerprint of the main binary function. Okay, how does it look like? So these are the two famous papers in the first place that reported the famous, the very important properties of the entanglement spectrum. One is about the spin-1 Heisenberg ladder. They prepared this periodic boundary condition ladder. So we have a periodic boundary. Cut the system exactly into half by cutting all the runs altogether. And divide the system into left and right. And then what happens is that the density operator would give the entanglement Hamiltonian in a way that the spectrum looks like. So I don't know how much people are familiar with this kind of spectrum, that this is very mimicking the expectation spectrum of n equals 1/2 Heisenberg chain. This is the so-called Gibson, which is like this kind of a chain. And then we have about this. So it means that if we just cut the system and then we focus on the left-hand side, the spectrum is going to reproduce the spectrum, the Hamiltonian of the right left-hand side. And this is actually done. Okay, it looks like mine. And there's another work that signifies that in the entanglement spectrum is very useful. This is about the Hotta chain. So the Hotta chain, as well as AKO, belongs to the class of so-called symmetry protective topological space, SPP. And this was a paper which, one of the first papers that proposed this notion of SPP chains. And what is the topological instrument? They have an nested. If you know AKO, you know that it's a nested equals one chain. And if you see that if this n equals one chain is like having an open boundary, we have like idle spins s equals 1/2 on both edges. That they will just have a 4 degenerate. And this is going to correspond to the S-state of. In that case, we find their entanglement spectrum by cutting the s equals 1 chain into half. You can see that all the entanglement spectrum, all these levels are doubly degenerate. And this is a signature of the STP. That's a very rich group of having an STP space. Okay, so you can probably understand that entanglement spectrum is very important. Now let's go another way to see how the entanglement property or the Schmidt state described in the analysis. Because so far, I think half of the people here are familiar with them, half are not. And those half, what expensive things, are only familiar with the way they do the spectralization for the expensive type. But we can do it for the permanent. Okay, let's just think about the 3 elements and do the spectralization. Now we have a list there first as a preparation. You know that the C beta C beta C C, an expectation value of 4 over. will be factorized into the product of the two body and one body, two operators. You know this very well, right? You are using this for the expression of this one. Okay, now this kind of one body C operator is evaluated also in the low density matrix. It is found. So it means that just remind of the shape of the local density matrix in A, like this. And then if this kind of thing will hold, it means that the correlation matrix, which is consisting of a combination of C delta C, different lex I and J, which forms like a square matrix, is going to be diagonalized into the form of F delta F in the same representation as those given for the entanglement Hamiltonian. The entanglement Hamiltonian is diagonalized in this way, so as a correlation matrix, the same operator. So it means that if you could like construct this F delta A in the expectation value form, which will give this theta as a diagonal value, we can also describe it in terms of the trace of F delta F times rho. And then you can see that this is a one-body problem, so that you can just reduce it to by just like subtracting just by deleting all the parts which are not related to L in this solution. And then you can get this expert, you can get this form. Finally, this theta equal to this form will give you the fact that the entanglement spectrum will be related to the correlation matrix eigenvalue. That we can derive the correlation matrix expectation value using entanglement spectrum. Okay. Now this is a periodic simple system. And we just go to the eigenstate of the three planets. If you know the type binding model from it now, we can construct this type binding Hamiltonian in the diagonal formula reciprocal function. Let's set the first level here. And then the many body state of this free feminine is a feminicide. So we just fill in all the levels below feminicide in a manner which we can be constructed in a product state, the operating data, because DK data is going to create all these each levels below the feminine. Now this DK data is fully transformed of the original Hamiltonian in the real space, C data. Right? So, but because this is a plane wave, it will distribute all over the system. So there is a component of C which is belonging to A and belonging to B. So we can divide the contributions of the data into A data and B data on how which is the original like a contribution from the real space in A and B. Right? Now, then we can also construct a correlation matrix D delta B for A and B separately, with the indices being a K space, like P and Q are like some reciprocal aspects, reciprocal vectors. Now, then, because this Fourier transform is simply a unitary transformation. So if we were able to do the diagonalization of the C delta C in this slide to get this theta being the diagonalized values of the C delta C correlation matrix in real space, it means that we can also do the same game by adding another like unitary operator extra to get this diagonalization of this FA and FB in a way that looks like this. Here, we put the eigenvalues as theta and 1 minus theta because in the original D, we had the index K, which has the expectation value of this like number operator at level to be equal to 1. But if we are dividing that into A and B contribution, so A contribution is theta, the B contribution will be 1 minus theta. But anyway, we can diagonalize it in this way. And then the fermions in A and fermions in B which in real space can be after diagonalized, can be like denoted as F dagger and B dagger. I just make different marks to discriminate domain. But then this F dagger and B dagger can be described using the diagonal from as a conversion from this original D case space using this transformation matrix like this. Okay. And then you find that, okay, if you want to make the filmacy again using this real space representation, just such that you have F dagger multiplied by the square root of theta and B dagger multiplied by the square root of 1 minus theta, put together and make a product statement. And this will exactly give you the analytical form of the Schmidt state in the fluid system. So this is the like a basic ways of constructing the Schmidt state in a phenomenon. Okay, this can be done not only for the type magnet, but for also the one-body mean field state, as far as the interacting state. So it can be a very simple way that we do the significant system in a one-body language. Okay. So far, I hope I have this fast. Is it fine for you? Okay, we'll go ahead. So we're ready to dive into the numerical and embedding theory. So now it's very funny that like you see that dynamical mean field theory has MF, and it's only one character that differs, but the original words read them. So like you need to add one more and get abbreviation. So what do we want for this theory, EMT? So we again go back to the case where we have a large system and divide it into A and B. Now here, A is much smaller than B, okay? But we know the full wave functions of this. And if we know the wave function, which is the guiding state of the Hamiltonian which we want, okay? And then what we need to get the information on this wave function is that we mostly need to know the local density matrix in region A, because, for example, if we want to evaluate the energy is extensive. So it can be evaluated locally in region A, and just by multiplying that energy density by n, we can get the. So the only thing we need is a local information which is precise enough. And the thing is that if the total wave function is very precise, the local wave function could be precise. But the local information here is like stored in this small density matrix with small long dimension. The trick here is that, okay, we only need this guy, right? And then if you have like a proper total wave function, and then we can get the local information very precisely. But this is just an assumption. We don't know whether this is going to be precise or not. So how to get a good local density matrix in A is the question. And we very trying to optimize the local density matrix in A. So how do we do it? So we again go back to the Schmidt decomposition. We just divide the system into A and B and do the Schmidt decomposition. And if the size of the A is small enough compared to B, the maximum, maximum numbers of Schmidt values, which is non-zero, is bounded by the dimensions of the local space. So if we make A small enough, we can just treat this problem in a very small numbers of memories for the information. But then here, you can just see that this value of the summation is not maximally bounded by the dimensions of A. The dimension of A is very small. But then originally, the state in B has lots of information, which is like spanned by the Hilbert space of B, like D to M B, right? But then we have to select the counterpart that will couple A, which is a small number, from that very large numbers of basis originally appeared in. Right? So how do we do it? So there's not an actual and exact guideline to do this kind of treatment, but DMET borrows the idea of the DFT calculation empirically from Louis working. And because I think that Garnett was basically a quantum chemist. So I think he's influenced a lot by the idea of DFT. Then let's just go to just explain the underlying concept of the density functional theory. This is the initial theory. And there's a famous work what did that. So density functional theory. So what's this function? I'll just tell you the basic idea of this density theory. So yeah, we have a many body state interacting electrons in a very large system. Like they have like bunches of atoms and levels, which are very difficult to solve. Right. How do we do it? So then the density functional theory relies on the quantity of charge density distribution function. So suppose that we are given a proper charge distribution function in R. Then we can define a thermodynamic potential as a functional of the charge density distribution in R. And this can be done by straightforwardly evaluating the Hamiltonian, including the kinetic term and interaction term, by the density operator law, and also the entropy term, and also some extra one-body potential term. Now, this law, density operator, is minimized in this form to get this omega to be lowest in energy for the given distribution function of it. This is the thermodynamic function which we want to get. Now, but we cannot do this because this H interaction is an interacting Hamiltonian that we can solve. So how do they do it? So they prepare a reference system with a fictitious one-body potential being effective. Here, the difference between the true thermodynamic potential and fictitious reference thermodynamic potential is such that the Hamiltonian includes only a kinetic term. There is no interaction term anymore here. But there, they add some one-body potential, which is the fictitious potential. But it's a one-body, so we can solve it, right? And then, the idea of the density functional is such that the Coulomb-Sham scheme assumes that if you could properly choose the V effective in this reference system, the lowest charge distribution function in R that will give the lowest reference omega will mimic very well to the true thermodynamic potential, which then the true charge distribution function that will give the lowest true thermodynamic potential. This is our assumption. And based on this assumption, the density functional theory does the work by comparing these two systems and to do the a variation in terms of the charge distribution function to determine what kind of V effective it is. So that's the strategy of the density functional theory. So then the DME here is going to borrow this idea. So in order to get a good density operator in region A, we want to optimize the basis. For that, he introduced a reference Hamiltonian. And here, this reference Hamiltonian, the original type binding term, is called the fictitious one-body potential term. This is a general 2x2 matrix form, which can be written in a one-body. They are the parameters. Okay, then once we just determine this reference Hamiltonian, we can, of course, calculate, because this is a one-body Hamiltonian, we can set the whole system A plus B to be very, very large, but we can still solve this problem and get the wave function in a very large scale. And then once we get this one-body Hamiltonian, which is very large, we can project, we can just make a Schmidt decomposition to just make this restriction of the reference Hamiltonian in such a way that the impurity in the last state will be divided, and each of them are like combined in the monomatic. Once we do it, we know the form of just as I did just like in a few slides in a fermionic case, we can do something for that, and we know the speed in analytical. Now, once we know the speed, we can project out the large Hilbert space, original Hilbert space of the subsystem B into the small subspace by this operator using the Schmidt state in B. And now using this projection operator, we can construct the impurity Hamiltonian from the initial Hamiltonian we want to study by this projection. And then once we get this impurity Hamiltonian, the very small size Hamiltonian is many body in a faithful in many body solver. Right? You can use it, you can use something else, but you can use it and you can solve it very precisely. And then you get the impurity wave function. And then the lowest energy eigenstate of the impurity function will give the optimal, like ideal state if we choose B to be a very proper state. Okay, this is the main idea of the Yes.
So in principle, distributed convolution, the integral will flow exponentially flow logarithmic to be with the system size. Okay? So it's sort of restrict the size of it.
But you see that this is a more interactive system. So you can make a Schmidt convolution and keep the size of A to be small. You don't have to care about that. You can only, I mean, you don't have to treat a, super large scale. You just can do it in a size that we can afford in. If you just get 8 sites for the impurity site, we have to solve the problem of 16 sites throughout, right? And then they can still solve by ND, right? In that case, entanglement is not so large, and the Hilbert space is not so large. That's the advantage.
Right. So I guess my question is, yes, when A is large,
yes,
then you cannot truncate it too much.
A is large, the practical construction of this common that is going to be blown up. So we can just make this Hamiltonian, but it cannot be solved anymore precisely. So that's the point. So we don't treat it, but still we can say that the size dependence of the result in terms of this impurity size plus more. So we have to worry that much.
So we assign P is a complete set. The in projector P, yes, they're not a complete set, right?
This one?
Yeah.
This is up to
the sum of N.
Some of them, yes.
Yeah, that's a complete set for P.
This is going to give a complete set.
What's the difference between identity?
We use this identity because there are several variants. And previously, the first paper used this not as an identity, but as a Schmidt state of A. But it's only an inter-transformation from that identity. How to do that? We do the Schmidt configuration, right? And then, because A is kept, the original Hilbert space of A is kept as it is. And the B, we have a large Hilbert space. We want to shrink it to the size of A. And for that, we use this one. But then we don't deteriorate any information in this projection because we only focus on B. We lose the information partially, but we don't care about B. Of course, B has originally a large Hilbert, but it can be shrinked to the size of A because if we need to make A precise, we only need information from B. But if it is precise, it's going to recover information in A. That's the basic idea.
So we reduce the dimension of original.
The dimension of the subspace is reduced, but the information on it is not. Choose as a as this wave function and very exact translate. You just do the Schmidt decomposition, right? And then you can evaluate this local density objects very precisely, right? Just the problem is that we don't know the exact part. So we mimic it by using this. We cannot, this will guarantee the quality of this part. But if it is of good quality, it can reduce the glass in very precisely.
So what's the difference if the effect with reference space in the reference system seems like a mean field?
You need to have a loop.
Yes, exactly.
You have a way to the loop yet?
Not yet, because loop is a bit like, yeah, loop to the loop, but try to see.
Also, it's worth to notice that this side B is not complete. It's enough to.
It's a projector is not complete.
Yeah, it's
based for the B. Must project out certain state. The subspace of T.
It can exactly represent your boundary. It's not a complete sense.
So I think it's quite a poor outcome here for the first. The difficulty is that, okay, this process is fine. As far as P is fine. So, but we cannot just, our selections of the reference we talk, this is one line, is nothing. And which choice of the each reference is being better for getting a better way? We don't know the discipline. This is because the method is not variational. So the lower energy does not mean the better solution. But we don't, I mean, we can just change the reference Hamiltonian slightly, and we can just derive for each given potential the solution, but we can get the energy. But the better lower energy the kind of input that is being discussed. But if you don't stick to so much the better solution, we can get a moderate solution. This is basically the root that we mentioned. Just define the boundary potential, and like so, it's in a very large system size, including A and B, and then just obtain this reference, then project the full Hamiltonian using the Schmidt values, Schmidt state in B, combined with the original state in B, and then construct the impurity Hamiltonian. And here we have to slightly adjust the chemical potential level in order to keep the filling of the impurity side to be off. But anyway, this is a detail. Obtain the impurity wave function from Hamiltonian. This is a many body quantum exact work. Then we judge the quality of the impurity, how good this state is. But here it's a bit tricky because there is no rigid cost function to judge which kind of state is better. So the original paper by Garnet was in these two cost functions, D, M, E, and B. So D, M, E, cost function is comparing the correlation matrix C double C obtained by the reference wave function to the impurity Hamiltonian wave function. So it means that it's not like self-contained, because if you just prepare this reference Hamiltonian, it's not that much different after the first guess. It means that that's their like logic, but it's not necessarily maybe the case. And DET is comparing only the diagonal element, meaning the electron number, evaluated by the reference system and the impurity. Anyway, these cost functions are the lowest ones, so let's go ahead with it. Now we just try to lower the cost as much as possible to get the reference Hamiltonian make in the local subspace A to those factor of solving impurity. And just do this loop again and again, and finally get the energy and local density matrix in the background. That's the pressure. Now, but during the time we were trying to implement from 2015 to 2018, there have been several. So these three papers first proposed by Hotta have several ambiguities. The paper has told different. But to his role because maybe you say that if you are like developing a method in the first place, you always encounter the details which we cannot solve, but the overall strategy should be fine. And then we test several things. And sometimes we come up with new ideas and test something else. But then the papers will be rather fragmental to just different things. And sometimes people will be confused. That's the situation. Actually, they are trying to just see how it works. They're like chemists, so they're like, if things are going empirically fine, they're happy, right? But we are physicists. We want to know the underlying structure, what is right, what is in principle right or wrong. That's legitimate. And then we started to try to solve this problem in the physics point of view. And there we have just fixed several details. Like, okay, we can just choose the empirical representation just as you questioned. We let the basis of A as it is, first place, instead of using the just state. We do need a chemical potential in the empirical side to adjust the filling to those who need to run. If you want to have a model, you have to put an empiricity to adjust the final level in the empiricity to get a proper solution. And also, we can also, if we need to improve the interaction in the back, it will also a confusing point that some part of the people was not this. Okay, but there are so have remaining questions still, so I have to just make demonstrations on how it works. The two questions still like not fully fixed are which cost function is better, the ET or the NCD? What's the difference? And also, what kind of potential in the reference Hamiltonian to use? Because we can come up with any reference Hamiltonian that we want. And then sometimes the potential could be like breaking the translation limit. Sometimes rotational symmetry. Or maybe it can be nothing, just a very symmetric potential. I don't know. And then we have to choose several things to test which is going to be better. But the question is that how to get kind of a feeling that we're doing right and which is better. That's really difficult. Because this is not the. But anyway, we just go on to this. So we just talk a bit more about the details. Okay, so I'll just talk a bit more about the details. So when we do the Schmidt decomposition, we just make we classify the three groups. One is the bath, which is coupled to A. Another is a core state, which has an electron filled in that level, but they're not coupled to A, but coupled only to inside B. And they're called correlates. They are also included bath level. And then we have an empty side which does not do anything about this structure. So we construct this bath side and project out the original Hamiltonian by this projection operator constructed by C, and get the impurity side, including the chemical potential. And we have an interaction term between bath and an impurity, and also a bath which has an interaction term. So we have basically 1 plus 1 plus 1 terms, 4 terms. And they are like quite a mess in their description, but it's just the description and everything is working out. Okay. Now, let's just review some early studies in the gardens. Okay, this is the first paper in PRL. They tested the Hubble chain. You can see that sometimes they're comparing the one-dimensional Hubble model with the other solution, which is exact. And you see that for some cases, the energy is falling below the other solution, meaning that it's not relational. This is a bit interesting because okay, we don't know like which is better. But anyway, they tested several things and saw that it was more area than they have also tried several things with the Hubble model, and they also worked quite well. And like this was the variations of the cost function and And then it looks quite different between different cost functions. But anyway, this was the first shot. Now, they have also tried to change the chemical potential to make the chemical potential curve, right? Try testing the functions of. Then you can see that at half million, they're going to have a charge gap, which is considered a log gap. So in one dimension, we have immediately opened the gap when we get finite view. But in DMFT and also in DMET, both cases, at half the length, there should have no phase transition. They immediately become a Mach insulated whenever we get a finite view. But in the one site DMFT and one site DMFT, both have a finite view critical, a bit wrong. But anyway, if you just go to larger cluster size, you can get one way result. This was what they were claiming. Now, so we wanted to do a more precise physics work. So we tried that many variants and tested and which was to be better. All the things are written in the PRB paper, which I think to be the final version. And then with this, we can exactly define the energy of subsystem A by including HA and a chemical potential term and half of the interaction term. Then you can see that the energy of equation A is exactly the same as the DM energy in this precision. Okay. That's a function of U. Right. And then we go on to test different variants of the cost functions and compare again with DM energy. And then you can see that the error of energy against DM energy is always positive. It means that in our construction finally, we are able to get the energy at least higher than the exact value. So right now we're safe. Okay, it's better, right? Still, the question is, which kind of function is better? Sometimes we have a bit of slight deviation between different functions and different functions. The potential here, we just get it in this 2x2 because it's a general form of the emission matrix, which is spanned by the Pauli matrices. You know that 2x2 matrix can be spanned by the unitary matrix and the Pauli XYZ. Just make it part of the isolation model. Then we can test. Let's go to the Hotta chain and see how the entire spectrum looks like. Then this top figure, both top figures are the entire spectrum. The second figure is the entire entry. And the final figure is the potential that we used. And you can see that the fingerprint of the wave function, namely the entire spectrum, works quite much well compared to the adopted data, which is the emerging result. So you can see that, okay, internal spectrums are quite well in the ETNCC version. But once we get different cost functions and different symmetries of potentials, you get a bit off. But still, the energy evaluated using all these mathematics are not so much different, almost like 10 to minus 4, which is not different, and you can just quite well serve solutions. So in the sense of electronic system, I think it's enough to get 10 minus 4. So then let's go to a bit more difficult model, including side interactions. Hubble model, they only have a one-side Coulomb interaction. Now we have an interside Coulomb interaction. So we do it with a TV model, but with spinless running. And in one dimension, it's going to be equivalent by the Euler-Wigner transformation to the X6D model. So it's going to be the result of the spin one half chain in the X6D manifold. So we do it for the nearest neighbor and next nearest neighbor interacting spinless premises for name X6D. And then we do the same game with the impurity cycle 2 or 6A. And then we find that you see that the entire spectrum has a perfect match with the energy solution. Okay, this is why the energy is given for 128 site, which is not very impressive. So I think this is one of the very appreciable. Now, also, the energy looks very nicely. And quite surprisingly, it was quite a surprise to me that Of course, the matching of the creation, the density matrix means the exact evaluation of the local quantity in A. But further, we can develop an evaluation of correlation function as a function of the distance R. This is a charge-charge correlation function. And you can see that, okay, we are taking the impurity side up to 8, but still you can see that there is a very good match between the DRG result and the DMET result. This we did not use the maximum size, but you can see perfect, almost a perfect match of the correlation function. So it means that this is a quite important message that there will be the advantages over DMSDRC. So, this time I think DET is a diagonal function. DET is the safest because they're reproducing. But now,
sorry, questions. What is the cluster size?
The cluster size was 2. And then I forgot this one, but I think it was like, the creation function, they are going, this is basically, they go further over the cluster size. So that side is a creation function, but still.
You just interpolated. Did you see interpolated?
I forgot, but this is exact. I think it's more usual tomorrow at digital. Okay, so the advantages of the DMT is such the energy is still like highly kept precisely above the variation of the anti-thermal spectrum is very precise, and the correlation function of real space is much longer in scale than the side of the cluster. So it means that it's not a cluster method, because you see that usually the cluster method has a serious cluster dependence. So the correlation functions are not precise, although we can use the cluster method. So I think this is a clear advantage. But there are several numerical issues. Now let's go to a much clear thing that usually in numerics, if we do the many bar calculation, we have 2 serious things that we have to put in. One is a finite size dependence, another is a cluster dependence. Okay, so if you have a state which has, for example, a long range order with a period that does not match the period of the lattice, it's going to be a nightmare. Because sometimes this kind of thing, the true ground state will be missed because they are underestimated in energy. And that's why we cannot cope usually with incommensurate orders or the wrong length in final state. So how does it work on that question? So before that, we are going to just show you some ill-defined examples. I don't want to be too offensive, but okay, so we have a Kagome-Hubbard model transition. This is one of the difficult problems. We have a Hubbard model of Kagome lattice, Hubbard model. And then we can increase the value of the on-site correlation graph, and at some point we get the transition to the state. The question is, what kind of state we get just after the mode transition? But then previously it was like argued using the cluster DMT that they have a chiral order because they have used the cluster in constructed it 3-site and 9-site. You can see that half-filled 3-site and 9-site are correlated to odd numbers of states. You cannot have like singlet. So it means that they automatically favor this kind of magnetic state. Actually, the correlation is developing in this way. But after that, it was tested by the method called VCA, which is also another cluster. Then with the cluster size to get even number, and then all these magnetic spaces will smear out, and we get the balanced mode types of transitions just after the. So we have to be super careful, choose the types of cluster and what to claim. We can just get a numerical result, but we cannot claim that it's going to be true before examining all the possible other possibilities to check whether it's likely to occur. Well, so this is one of the examples. Of course, there are some good examples that this kind of cluster method works very well, but for the frustrated magnetic sometimes. Okay. Another example. Which we want to have quite an advantage of another. This is a spin-legged material. And then there's a spin gap issue. This is the big idea, I guess. And this is using cylinders, right? And you just prepare a cylinder like this with a small circumference and make the length of the cylinder to be infinite. And then we get the aspect ratio to be very bad. And in that case, the inverse circumference dependence of the energy is going to be almost flat. But if you do the same game with like a kind of a rectangular cluster with an aspect ratio of 1, we get different scalings and different spin gaps. So, and I have also a similar experience on a one-night plateau, which is also a gap. If you use this standard cluster and do the class scaling, it turns out that the size dependence is going to be like changing at around the system size of 72. It's quite enormous. Then it's going to just converge to the value of the. But if you do with a cylinder, it's going to give a completely different value. So the way how we construct the cylinders will also always like influence the quantity of the result, not the quality, but quantity of the result. So we have to be super careful about how to interpret the result we got. And then, I mean, this paper I quite like this site. This is by Anderson, based on what Carl Keaton explains that you have to have a great care to just extrapolating all the size, in particular in acidity geometry. He was studying the Radisson crystal for that was claimed in the DMRT study to check whether it's going to be true using the model of and found out that if you take the length of the cylinder to 20, its results will change. So this is a kind of a good example that we have to care much about. Now, let's see how DMAT works for cluster-size conversions. So this is a paper, I took this paper from the quite early work, not a very enough for benchmarking the different, I think this is you currently right? Maybe not. Okay. But anyway, this is a 1D Hubble model, 2D Hubble model. And there's a cluster DMFT, other methods, and you can see that the DMET with this blue dotted curve looks quite well because they have less cluster dependence compared to other oscillating size dependence. So it means that, as I mentioned, the prediction function is working quite well for the DMET. DMET is good compared to other clusters. So based on this fact, we have studied the incrementally order base. This is the example, I mean, tells us a lot about it. So it's about the Russian spin of the model. It's a bit complicated model because the electron hopping will change its spin direction and hopping to its neighbors. And it takes the types of the Russian model. You don't have to go to the detail. But it's a Hubble model, just that the hopping is modulated, spin dependent manner. Now, with this Hamiltonian, we get a phase diagram like this, a rich phase diagram. But because of the spin dependent hopping, we have incommensurate ST pieces when the spin of the coupling is very small. Theta is very small. Theta equals 0 is a usual Hubble model experiment. Okay, then there had been a previous study and FT study phase diagram. There are 3 serious artifacts due to cluster DMAT. One is that in a theta equals 0 region where we have a sphere lattice Hapland model, we have to have U critical to the Mach transition to be 0. It's critically wrong because we have to start from 0. So this is wrong. Another thing is that they're claiming spin ticket. This is also shown analytically to be wrong. But then we find in our STW1 region, commensurate the magnetic base in their framework because it is cluster based calculation. So I think they are just trying to stabilize some artificial borders. So we want to test how their claim would be right using the ET. Now, so we prepared the same Hamiltonian and the fictitious reference Hamiltonian potential by putting two terms. One is the antiparamagnetic term, which clusters the EMFT pushing. This U field is an incommensurate borders which we are pushing. And then we just put all these potential tools together and just made the iteration on the and found out that this antiparamagnetic thing will just become zero or zero, and our case will be survived. So this I would use EMET as a proof that the strong correlation method will favor this. The spin density wave, which is having a nesting vector, which is in the incommensurate, very difficult real number. So this can be one way of using EMET. Yeah? DMFT was something like this. You mean this one?
Yeah, I mean, can you put it?
DMFT there, for example, using 2x2 cluster, and they cannot accommodate incommensurate because they are like so they are not good at correlations anyway.
Yeah.
So I mean, there's no way of getting out of this for that. So I don't blame them. Just that they are having the tax about they cannot. So, but DMET, they can always kind of difficult. Another thing, let's try to see whether we can describe the spin liquid. We're going to probably still have some. Okay, so we want to know whether we can describe the spin liquid. So a very famous example of the electronic system with the spin liquid is the triangular lattice Hubble model. We have a simple Hubble model with T and T prime, probably different in the vertical direction only. And then T and T prime of equals is going to be a triangular lattice. For T prime equals 0, it's going to be a square lattice. This model will interpolate the square lattice Hubble model and triangular lattice Hubble model. And this is a famous phase diagram of plane of T prime over T versus U, showing that at a critical point, you see, we find one transition here to the magnetic insulating field, which is considered to be a spin liquid. Because, as I think previously it was introduced in the talk, that you see the DMFT, if you assume the two-side cluster, they will just favor a one transition. But now if they assume one side, it's going to give you a genuine one transition. But here, they do the kind of study called PIRG. And they figured out that there's a genuine one transition, therefore that the study on a single side, that they're not driven by the magnetic waves, but there they only find a one transition, not waves, with a non-magnetic phase. Now I have just compared all different previous results, how they mimic with each other in a different solver. And I think this phase is right. But then there's a study claiming that we have a one transition here, and then another transition here to the 120 degrees magnetic order at around this point. So we want to test it, how it works with the machine. But then we found a bit of difficulty because we chose different cost functions and different potentials. And then all of them were mimicking in some sort of like energy, they mimic a lot. The W object, this is the W object, this is the W object. We found the transition at some point, but we could not find for a unique transition point, common transition point for different potential. And also some potentials favor only one transition, other potentials favor two transitions, but we don't know this to be true. So trying to first spin liquids is still a lot of difficulty using DMET. So I think it's a super difficult problem. Okay, so I'll summarize what we can do and what not do with DMET. So you put some proper details, the method seems to work very well because it does not like go, the energy does not go lower than the variation amount, so that we can safely just get the solution. But we cannot just which kind of potential function is better because the method itself is not efficient, so we cannot have any rigid ground on it. But still, it works quite well. So the advantages over other methods, particularly DMFT, is that it will give a perfect match on the random spectrum. And also the correlation function in space will be very well reproduced. And there's no cluster size on it. You cannot cluster size out. So there are always pros and cons for every method. Sometimes it's better to apply sometimes to DNA. It really depends on the problem. Okay, so I'll show finally introduce our organizers, Chang Min's paper. This is a kind of all-star paper comparing all the solutions on a two-dimensional Hubble model as a benchmark. It's a kind of a long paper. Probably numerical physicists will be very happy. You can see that the DMRC cylinders are accurate in terms of 4. They meant to be like this. So explain a bit of not very nicely. There are also some other benchmarks showing how the energy looks like. But this is not variational. But this paper is nice because they are putting all the detailed information and also which method is variational and which is not. So they are very detailed, and you can understand if you have good discipline, you can understand many information. You can see it. So there's several other works related to DMFT. I don't say this is covering all the works, but it can be applied, for example, to spectral functions, quantum systems, and rotationary invariants like that. Also, spare lattice, hydrogen chains, honeycomb, other systems are and there are also some pieces of information that might be useful for those who are studying hybrid models. So with this, I think we're done. So the summary is that, okay, I don't want to say anything about it. I have just addressed the experience of how we can cope with a new method, particularly when it is not well established. We can just test many things and just check how it works and what's the underlying idea of the method. What is a good point and what is a bad point compared to other methods. So thank you very much for your attention.
Spiral order.
Yes.
Did you formulate the MVP?
No.
Spiral.
This part is spiral. Information.
Right.
We did not. I mean, I think it's quite awesome to look at because incommensurate ones are always a nightmare for the cluster methods.
Yeah.
As far as I understand, it's not good to apply it anymore. So just try other methods for that purpose. So that's my intuition. Yes.
Yes. I think even some people formulate using spiral.
Oh, really? Okay, it might be probably discussing. Okay, let's see. Yes. Thank you very much for your invitation.
Yeah. So on top of the crosstalk size, there's another important assumption is the environment will approximate it magnetically. So let's say one of the errors from the cluster size. Another error I think is from the postulation that the environment approximated by a stated determinant.
Yeah.
And is there any system that this approximation is particularly convolutional?
In my sense, the important thing is not to draw important projection. I might have given an impression that during this projection, we were like using the Slater determinant solution. But this is not true. We are only selecting the basis. And then we optimize the graph also. So we just choose the basis that should be the graph. Does not drop too much information, it will work. That's the advantage. So we're just like, okay, you're just choosing doing anything wrong. We just choose the basis and project out P3 with this basis and target. So if this choice is not doing that much bad, it's going to give exactly how the basis will work for this true monotone in a many-body sense. It means that we're taking full account of the many-body effect as far as we are not dropping off the important basis. So that's why I think this method is working very well compared to other methods. Just not dividing a system really into parts. They are connected very tightly, and they are optimized there for that and very.
So it is like symmetry breaking and it's all the and then you have to have used a larger class.
That's for some. That's not so. Usually, if you have, for example, 3 sites in pre-evolution, you want to prepare a cluster of the multiples of 3. But here, you see that the correlation functions do not depend on the choice of the equal clusters. So it means that you are doing entanglement, not physically cutting out of the cluster.
Very specific my question because, for example, iPads, they use 2 clusters or even single site cluster. You still complete the correlation function pretty precisely distance, but you can never have symmetry breaking to 2 sides.
I see.
So
I see, yes. So if you have a symmetry broken potential in the verbal system, the result will be symmetry broken. If you don't use the symmetry broken verbal system, then the symmetries will keep in solution. But if you calculate a 2-point correlation function for both cases, they match. So you just don't focus on a one-body term. Only just like we do for example, if we do the open body condition calculation for the DMRG and the created body condition for the DMRG, OBC will not break the symmetry of the null site, and the OBC will break. If you calculate the correlation function, not large scale, will match finally, right? Not perfectly, but match finally. By for the boundary effect. So the same thing happens. So the choice of the base should be symmetric or not.
So the positional symmetry does not strictly include it in the argument, so it's still allowed.
It really depends. So we're showing you some examples in this one. So if you focus on line, if you see the difference, I mean, this SU2 thing, they are keeping the original symmetry, translational symmetry. And then the density matrix will recover the perfect symmetry of the DMRG, which is also translationally periodic. But then if you just prepare a potential, which is going to break the SU2 symmetry. And it's going to change your thing. Also, particularly when the final potential is finite, it's going to change. For example, this will fall off from the average curve because of the breaking of the symmetry. It's like but for some reason, they're keeping good information so that the energy is working very well.
How about the correlation?
Correlation is also probably, I haven't checked it, but in my experience, it worked well. So 2-point correlation. So that's a kind of magic. But
question about chemical potential adding on the impurities. So the chemical potential adding on the impurities.
Yes.
So is that used to control the feeling of the entire system?
Not, it's going to control the filling of the cyclate,
The
impurity cycles. Because we just project out, sometimes depending on the relationship with the valve, going to have an impact in the electron. Sometimes it's have a deviation, or have a larger, like without any electron impurity. We have a larger density of electron in the impurity side of the last side. So we have to just control them. That's kind of tricky thing that we have to figure out to the and sort of origin.
Question before you penetrate the section of entanglement, so we can repair the small size total. Then
This is a small sign. This is like this is the entire network, like I don't know how much.
So is that estimated? The impurity structure the Hamiltonian is that basis.
Yes.
And then so that spectrum of pure Hamiltonian is the same of the
Yes, this is the pure Hamiltonian spectrum. Finally, named after the calculation translation. We just found the threshold and do the calculation after it converges. The cost function converges. And get a final result, and that will be the empirical Hamiltonian put them in the entire spectrum, which is obtained by the projected Hamiltonian. Okay.
Understand again. And try. And please come back to the characteristic.
要把它关掉，或者说缩小。基本上。
Okay. Yeah. Oh. Yes.
Okay, so good afternoon. We are about to start the afternoon session. I'll be chairing this section. There are two talks in this afternoon. First talk is given by Professor Fujimori from NSRRC. And everybody knows Professor Fujimori is an expert in optics and weeks studies. And he will give us introduction to the optics and weeks of two-phase superconductors. So let's welcome Professor Fujimori.
Thank you. That's all. Actually, can't be organized as well. Give me the opportunity to talk about this subject of highly theoretical sport. My best to say, discuss with the same language, physics, which are studying. Let me introduce myself. Fujimori from I retired 5 years ago. Now visiting studying technology for university and visiting researcher in NSRC for years. So today, outline is a little bit just I mainly focus on or exclusively focus on the cuprates, superconductors, and silicate behavior and its origin studied by RS Weeks and quantum fluctuations, QCP studied by Weeks, and if I have time, vector of interest. And in between, I also would like to produce the basic concepts of unique arrows and rings. Methodological aspects. So, so first, maybe it's not necessary, a very brief introduction about cuprates. The superconductor consists of CO2 planes and separated by a sort of charge reservoir or drop planes. And the phase diagram, we have already seen this phase diagram many times in this school, but the undoped, starting from undoped multi-shader, carriage dot apparatus quickly drops and superconducting phase appears and finally disappears. But many researchers are interested in the origin of the pseudogram. This is some mysterious phases, or we don't even know this is phase or so. And also strand metal phase, which resistivity is quite unusual. Folks gave a very nice theoretical talk on this subject. And the material is, as I mentioned, this is simple but still quite complicated. Many copper has already 5 orbitals, and oxygen, each oxygen has 3 p orbitals, and there are many oxygen. So the starting point is this is so-called downfolding initial band calculation by Hotta. Originally, we have 17 energy bands from these many orbitals, but in many cases, we reduce the number of the downfolded band into 3, and so-called 3-band model, which consists of bonding, oxygen, copper 3D, x square minus square, oxygen xy, bonding, anti-bonding, and the oxygen non-bonding states. This is a big simplification, but still it is too complicated to treat strong correlation. So in many cases, theory works for using a single band model. So with only anti-bonding band and downfolded parameters like this, but analysis of spectroscopic data also are made by using this simplified model with a hopping point 3 to 4 interaction 3 to 4 electrons. So this is a successful analysis of spin wave undoped pyramid compound, and using the parameters which I just mentioned, one can get super exchange 100 something milliamp volt, and also including actually next nearest neighbor ring exchange included. It was good agreement. These values produce very well exchange. And our first data. This is a schematic presentation of RS, and very nicely fitted using this this hopping parameter P3 and frame surface, corresponding frame surface. But there are this simple type binding fit does not reproduce two. Actually, this region of I0, the band somehow become very dark or disappear near the I0 point. So gap or kind of pseudo gap opens in this I0 region. So let me briefly show you what the unresolved emission spectroscopy looks like. The angle integrated mode is nothing but the Einstein's photoelectric effect. Electrons emitted from here separated from the chemical potential by the binding energy is emitted to the vacuum. We measure experimentally kinetic energy and calculate initial energy positions. In angle integrated angle resolved photoemission, we also measure angle of emitted electrons. By using this angle, we can immediately calculate the momentum. Momentum is conserved parallel to your sample surface. So we measure spectral function times pyramidal function. So the band structures cannot be observed above the Fermi energy because pyramidal. But I will show you effort to study these empty states. Of course, using Rig scan, excite electron, occupy state, empty state, but even RS we can do some tricks to study empty state. I will show you. And so this of states is nothing but angle momentum integrated spectral function. Yeah. So this is how this instruments works using a so-called hemispherical analyzer. Emitted electrons go through the lens, the reflected hit the detector. Then we can measure this intensity distribution in this way. And then we detect the peak here and rotate the sample a little bit then cut becomes different. And again, we detect the peak in this case here. So by connecting these peaks, we can get the bar structure or plane surfaces. So, and so effect of electron correlation is so within the framework of correlated frame rigid, this is a non-interacting energy bar given by density functional theory. Is infinitely sharp peak across chemical potential momentum. But once you switch on electron interaction, this spectral wave is reduced from 1 to 2. And most spectral wave is distributed at higher energy away from the chemical potential. So the momentum distribution function jumps because it's reduced from 1 to less than 1. So the realization pattern. But still the quasar particle peak intensity is infinitely sharp. This different from pseudo. So first we consider momentum independent part of self-energy. The other part is linear energy. Imaginary part is omega squared. And then the spectral weight is reduced by from 1 to the z number less than 1. This pattern becomes weaker. Then additional lost spectral weight is distributed at higher energy. But if self-energy is momentum independent, then this density of states is not reduced by electron correlation. The spectral weight is reduced to 1, but bandwidth is also reduced. So density of state that experiment doesn't change. So you need to introduce some momentum dependence to extract to realize the pseudo gap. So this pseudo gap momentum dependence can be any fluctuations, CDW fluctuation or CW fluctuation, because self-energy should have this kind of form where momentum is there. And Cooper pair fluctuation form is different, but still momentum dependence is there. So then let me overview this how the pseudo gap was observed historically. And so these are pseudo gaps. Spectral weight is taken away from the original finite value. But in the superconducting state, has different at the D-wave superconducting Hotta parameter. So if parameter as this form. And if you plot the superconducting gap as a function of the parameter, this becomes a straight line like this. In the superconducting state, additional gap increases near runtime of the region because gap was already there before superconductivity sets in. And let me come back to the normal state. And, as a function of doping, what we should regard to overall method. If the system is a normal ferroliquid, superfluid density, all concentrations is the electron concentration, Fermi surface area is constant, but slightly decreases for doping. And the electric specific heat should diverge near more condition like this. But that actual experimental data all looks quite differently from below 20% doping. Superfluid density decreases, drops, all coefficients. 1/4 coefficient or whole number equal to the special decrease. So in this region, system looks like the system develops gap or dropped in the density states, and that's what in this region. And so these are pseudo behavior. And then let me come to the resonant emission. Resonant X-ray inelastically X-ray scattering to study different aspects of qubits. So in principle, resonant inelastic scattering can be done at any elements, including 5D, 4F, uranium, but in many facilities, especially for our purpose of studying qubits, we utilize the KH light element, in our case, oxygen. The binding energy is 500, and LH or 3D junction in the present case, copper, and the energy region is in the soft X-ray region. So you using such soft X-rays, one can excite an electrons from whatever copper oxygen into empty states by absorbing photon, soft X-ray photon. But immediately after that, this borehole is filled by transition electron from some occupied states like this. So, so we end up with electron and hole pair. The momentum, energy momentum, this electron hole pair excitation is by energy and momentum observation. I can know these numbers by measuring emitted soft X-rays. And this is a schematic view of the spectra. Elastic peak, zero energy. This is important. Static information. And low energy magnons, bimagnons, and higher energy plasma. And then electron volt scale, there is a interband electron hole excitation and higher energy DD excitation and interband and many different excitations. Maybe I should mention this interband DD excitation are closely related to this picture, but phonons and magnons are collective excitation. So we don't need electron pair, but magnon and phonons excited by this process. And this is beam line at NSRC led by Fujimori and has been commissioned several years. And it's a very big machine. Of course, synchronous cells. Emitted electron and emitted photons are measured by moving this long arm at different angles. And the resolution in SRC is the highest in the world, especially KH. So this is a schematic view, scattering geometry, and incoming photon scatter, scattering up, incident angle scattering down, and scatter polarization. Scattering amplitude is given by lowest order is combination charge scattering, magnetic scattering, given by this polarization. Photon incoming and emitted polarization. But you can, I will not talk about in this lecture, but we can do magnetic scatter by choosing this polarization. Changing fixing the scattering angle at 90 degrees because by doing this, sigma incident sigma polarization does not exist anymore. And so also pi this and this becomes orthogonal. So charging scattering completely suppressed. So this geometry can be used to study magnetic excitation. And here I will focus on charge excitation, primarily using oxygen KH. Oxygen KH has a no spin orbit splitting. So this excitation by itself is already spin should be observed. I think it's excitation. It's It's a typical. This is, I think, the first observation charge order CDW witnesses growth. So a short-range CDW detected using bricks. And by using DD excitation as a reference, the elastic excitation is enhanced at some momentum in this material. So YBC of 0.2 or 0.3, or 2 pi over lattice constant times 0.3. So three unit cell periodicity. And in our data, LSCO, the momentum is different of the 4 times lattice constant. Strong peak here, first short-range CDW. There's also an anomaly. So charge order, yes, like this in the cubic phase diagram. Real space picture is like this. Periodicities around 4, maybe 3 or more. And but different material shows different dying temperature. So now let me go to origin of the pseudonym, which is the main topic of my talk here. And so there are many different proposals for the origin of the pseudonym. CDW I just briefly introduced. So translational symmetry, periodicities, or lines longer, or nematic order, which is rotational symmetry breaking of rotational symmetry. C4 rotational symmetry is reduced to C2. This has also been proposed. Electron fractionalization. This is produce no symmetry breaking by itself. Probably in the origins due to strong correlation. So the origin is quite reversal. And so also Cooper pairing can reproduce fractional Cooper pairing pseudonym. So this is schematically drawn here. CDW, depending on the system, occurs like this. And nematic order, similar to CDW, like this. And electron fractionalization, actually, this is most robust and goes to higher temperature and lower doping. So more or less close to the pseudogap phase. And the important Cooper pairing occurs only just above the superconducting phase. So let me look at this different scenario one by one. So that you are welcome to ask any questions to me.
Excellent question.
Yeah.
So experimentally, how do we determine T-star line?
T-star line. Yeah, it depends on the different. Okay, very good questions. In some cases, the resistivity and the resistivity deviate in this region. So T-linear deviates downwards in this region, and the nearest effect is enhanced below this T-star line. I think it's really tricky and depends on the research. And photo emission, of course, the loss of spectral weight. There are not many measurements, but you can see the changes, how the gap closes. And also STM shows below DC sharp peak, coherence peak. This is broader above PC, but still remains a broad peak, and finally disappear. Then the final point is considered. There are actually many time reversal symmetry breaking. Channel balance. Explain this. But he claims there are experimental data which shows change T-star. There are many.
Speculative measurements is there to constant peak.
This,
Yeah.
no, it's
Can we speak about the situation?
yeah, so the Chandra referred to one experimental work, and they no pronounced peak and maybe a break in slope or something. Not to second order. Higher.
Remember, there's some mental measurement on spin susceptibility, showing spin gap. And the T-star line is the it's spin gap.
Yeah, but I forgot to NMR, especially one over T1T, is sensitive to susceptibility at this susceptibility drops suddenly below this. Yeah, but this brings an issue that should gap with charge gap. So it's another issue. So charge gap opens, then spin also should be gapped. But NMR sensitive to spin susceptibility. Tools of that history. Fully follow. But then any other questions? Then let me go look at this one by one. CDW order. Just mention that CDW is not long latitude. Peak is black peak is broad. It's being observed, but at different temperatures, depending on different materials. And this was first reported for LSCO as a sort of stripe order. And actually, order spin around high pi. And so spin periodicity is so this to this is spin period, eight period, and accompanied by a charge periodicity 4. This is 4 CDW. And this is stripe. But also, so this stripe is slightly different from this charge order. And in charge order, each star is also slightly different. And charge order depends on system. Each star is also depends on the system, but only very weak spin, and there is no clear relationship in charge order and cylinder. This is a compilation of charge order, same phase diagram, and periodicity, wave vector, short range order. LSCO increases with doping, but the other system decreases. Okay. Because the other system are pure charge order. This LSCO, as I mentioned, very special spin charge order. Although this was discovered historically, first discovery of charge order because of the involvement of the spin. A bit special. It's more universal charge order. So my conclusion is this: CDW is not directly related to this star. And the kinematic, the rotation, so rotational symmetry break. This has been a hot topic probably until a few years ago. And I first observed as distortion of neutron peak at high pi, spontaneous distortion. This should be symmetric, but experimental data are elongated. And also, SDI shows this striking base as a different Fourier transform, as different intensity along this line as X and Y directions. So there are also transport data, excess speed data, and they show symmetric rotational symmetry broken region. Similar to CDW, but this does not go to high temperature low doping. part is another concern is that to have a pseudogap, you have some momentum dependence, CDW, pair fluctuations. But this doesn't break any translation asymmetry, meaning that rotational symmetry is broken, but there's no momentum dependence. Kx and ky become inequivalent, but periodicity is the same. One that's constant is still periodicity. So, in that sense, I don't think this can produce a pseudogap. And the electron fractionalization, we want to frame the pseudogap here. And the symmetry grading is not happen at high temperature until different for the CC. So the concept of electron fractionalization has been the literature for very long time ago. This is a schematic picture of the multi-iterator. And when you don't hold, the new states is created, which we call the in-gap band about the lower coherent one. And there is tiny dip in the nested states, which is pseudogap. So the phenomena is very general. And actually, all the numerical calculation of about shown by photo. So it's not very clear on this plot, but if you look at the paper, you can see tiny gap holes at the pyramid near Isaac. Magnitude is something like that. So right of that magnitude. So more recently, Imada group did cluster EMXT on Hotta model, and this is a blowout of this region, 100 dB. Lower Hotta band split the original lower Hotta band here to gap band. This is the result of numerical approach. But they identify there is a dark fermion because their calculated Green's function can be approximated by a free particle Green's function plus self-energy like this, which diverges after this red band, that fermion band, because self-energy diverges. So the quasi So energy divergence. So spectral weight is suppressed to 0. So this is dark in the sense that it cannot observed by photon emission or IG spectroscopy. So that's why they permit omega D in addition to omega C. Hybridization between this, actually this term, the delta K is a hybridization between low Harvard dark permeable. So bonding bar, this is bonding bar, bonding bar in gap states. So they call this two-component permeable model. But this is complicated. Spectral function is a result of complicated many-body process. But this picture is the same bond as no interacting to fermions hybridize through this hybridization term. So that's one way two-component fermions. So the schematic picture is this is potentiometer separated by U and what gap. If you don't, the system falls, then coherent dollar is nearly half filled. But there is the dark fermion parts. So it's hybridized through hybridization term and open the gap by 0. This explains pseudo gap in by 0. So the interesting point is that we have a pseudo gap in the nodal directions here. Nodal direction is always there's no gap. And premier remains, but if you can look at above the frame level, you may be able to see a pseudo gap. This is a prediction. And so pseudo gap is you scan normal belief is that the pseudo gap closes around the premier nodal direction, but actually pseudo gap is there above the chemical protection, but we cannot see because others cannot see it. You see, there is a Hotta's study some time ago discovered. This is theoretical prediction, cluster DNFT. Gap twist along the node above the frame level. And already quite low. This Peter Johnson could try to look at the gap above the frame level. This is maybe this shows gap above the frame level. But along the node. Probably it was not successful. But suggested pseudogram every not only anti-node. Node. And so so if you introduce Cooper pairing, then this pseudogram pi zero decreases because Cooper pairing and pseudogram competes. So so the component premium predicts the reduction of the pseudogram in the superconducting state. So this is what our group in the SRC try to detect experimentally and by using PICs. We use 2p excitation and interval electron hole excitation. Let's see. So let's see. Zoom into this. And as I mentioned, the normal state gap is large and superconducting state gap is small. So if you make a electron hole pair excitation across this gap region, then excitation is enhanced in the superconducting state. So we can tune the excited electron by changing the Hotta energy. Here, and the momentum is fixed. So we can excite here from here to here. So we can make change the Hotta energy, excite electron at higher energy. Thank you. So so sorry.
The dispersion for the dark
Yeah.
space independent of the volume.
Should be independent. Yeah. So we fix the concentration. Holding level. Yeah. Yeah. I think it's changed. Original one. And original one depends on the doping. So that period one is ad hoc notion. Cannot assume a priori to describe anybody spectral function. So I believe the that Fermi part also changes with those. So many this. So all these transitions have the same momentum because of that zone folding. Momentum looks different in this space. Same momentum, and at this point, the gap is in the superconducting state. Gap is becomes smaller, and then excitation intensity, scattering intensity increases. These are theoretical prediction in the superconducting state. Scattering intensity is enhanced. These are expected data. Changes suddenly, but below TC it is enhanced because pseudographics compete with the superconducting spectral wave is taken on. To check further, this we also look at the overloft region where no pseudograph opens. Then spectral intensity. I think this is spectral intensity I just mentioned. Sharp clear change about the T star. This temperature dependence is almost flat. So superconductivity becomes spectral weight in the scenario electron fractionalization. So this part is due to the Cooper pair fluctuation, but because of the time that we keep and go to the this is conclusion pseudogap. In this region, electron fractionalization is necessary. Slightly above TC, the Cooper pairing is responsible for this is momentum space. This is quite anisotropic, strong gap opening opposite direction. This electron fractionalization gap, pseudo gap, is in all the direction, option and diagonal. All that direction also. Then fluctuation let me charge it. But this time not all that part, classic part, fluctuation part
by charge using charge scattering. This is our entire data for LSCO. As already mentioned, there is a sharp, strong charge order peak at 0 frequency, elastic peak. But if you extract the 0 frequency peak, still you can have finite intensity at finite energy, which is delta. So there is a fluctuation of CDW, not only static short-range order, but dynamic CDW fluctuations. And so this dynamic fluctuation is approximately given by, it's proportional to dynamical charge susceptibility, which is modeled by this formula. And so this finite gap increases with temperature. Also width also increases with temperature. So this increase in width is approximately linear temperature. So maybe related to the T-linear behavior. Let's see. And if you look at the temporal momentum dependence and to observe what's happening near contact critical point. Here we are. The work is not yet complete, but this finite excitation, as you go from away from the, sorry, this is away from the QCP, X equal 0.2, the excitation gap, as I already mentioned, is finite. But gradually decreases. This is consistent with divergence of operational length as you approach from QCP, away from QCP to near QCP. But this raw data shows somehow signal looks suppressed as you approach QCP. It's because the scattering rate is enhanced. Scattering rate is dynamical charge susceptibility and enhanced, increase. We don't know exactly why. It's speculate that superconductor competition with the superconductivity becomes important as you go approach. This is the supergrid density. So black dots is supergrid density. The green curve is right-hand column. This is quite complicated. As we approach QCP and correlation lengths may diverge, but at the same time,
the superconductivity is enhanced because superconductivity in this region is compete with charge over. So superconductivity is, in a sense, suppressed in this region. Maybe you can see a dip in TC. So suppression of the superconductivity recover charge order. I don't know which is which, but then charge order disappears or goes to zero. Then superconductivity recovers and suppress the CDW even further. And, then thank you for let me go back to the electron fractionalization scenario, electron activities. I have already shown you the component model and the electron fractionalization photo difference. Like this, here only I0 and I1 direction. But in the electron volt difference is slightly different. Assess that the anticlimactic phase is bigger. And probably because of that, the frame surface is very different. Now, especially in the underorbit region, electron pocket appears around I0. This is believed to be due to anticlimactic ordering or anticlimactic short-range jobs. But let me interpret these results in a two-component Fermi model. Then, as in the case of photon difference, now the in-gap state is formed just below the upper Hotta. And through hybridization with that fermion, gap opens. Pseudo gap opens here and here. And this picture can I naturally explain the electron pocket at I0 this slide. And big gap below the chemical potential in northern direction. So as I mentioned, there's a pseudo gap in the northern direction in photon difference, but no one has seen this. But because we changed electron hole are exchanged now, we can clearly see the pseudo gap in the northern direction. And, but the interpretation of this this kind of spectra and this version of this frame surface has been made in anticlimactic pseudogap, which open anticlimactic Brianzon boundary, the constant gap between the two folded bars, different bars. But our data are slightly different. Our data gap is not constant. Graphs near I0. And actually, cluster DMST calculation shows collapse of the gap here. They're very different from simple arithmetic without the one. So we plot the momentum where the pseudo gap appears. Momentum space. Yeah, the pre-reference space, and not exactly at the diagrammatic realism. So results are quite similar in diagrammatic realism and diagrammatic pseudo gap, but if you look closely, many different can be observed. We attribute it to began explain this difference by so by that sense, similar picture photo difference of electron fractionization. So this is summary. Yes. Professor Riggs very hard to investigate conventional supercomputers. And these are concluding base diagram. This part it's electron fractionization is the origin of pseudo gap. And yeah, contract critical points. CDW fluctuation, which is very interesting. And you form and I think our time to mention quickly mention this part to fluctuation. Good part. And finally, the electron dot difference can be explained by the same scenario. Thank you very much.
Thank you very much. Yes.
It's invisible, so that we should rely on the theory. But theory prediction is that there is a no bias. And it is in theory this is divergent energy. Experiment.
Yes. So the specific enhancement in star.
Yeah.
It's more associated with value calculations or calculations.
Which parts?
The gamma coefficient.
Yeah.
It's singular near the star. Is it related to CDW or not? That a question?
Yes. Which experiment?
The specific heat.
Specific heat.
Heat.
Yeah, 90% in Asco. It's like a very strong particle.
This is low temperature gamma temperature. This is doping. And this is around 0.2.
Yes, this is
There's a huge peak.
yeah. I think this is mainly due to bubble signal.
Oh, right.
To LSTO. That's just obvious. And the position changes will be and they are in European change it.
For what ECO and other filtration is very far.
Yeah. Still research. I don't think so.
It's not
I think
clear,
for us.
But for other compounds,
the claim is the compound they study is
still enhanced.
yes.
For other compounds,
Yeah.
they're still enhanced, but not that sharp.
Yes.
Just a pump, right?
Yeah. Probably other compounds are more. Because NCCU was special.
Okay. For experimentalists, audience, or serious, any questions? So allow me to ask a question regarding the electron fractionalization to explain this pseudo gap rate. And there is a very popular view to plan the pseudo gap in terms of Anderson's RBB.
Yeah.
That was long history.
Yeah.
So popular view is that pseudo gap is mainly driven by some kind of reform Hooker pair, which is a spin singlet between nearest neighbor electron. And suppose we have such a spin liquid, RBB, and this is D wave. Okay, and theoretically, people study this kind of a linear theory of a TJ model. They could get the T star more or less following this T star line. And also, from this simple linear theory, they could get the the Fermi arc near these nodal points and gap around any nodal region. That is because this is D wave. For D wave pairing, the nodal points are gapless. So you may have a coherent quasi-particle P. But near the antinodal region is fully gapped. That could explain why, in the whole dot case, you observed the pseudo gap more along the antinodal region, but you observed the Fermi arc around the nodal points. And this popular view may or may not be related to the electron flexation or dark fermion that you mentioned.
Completely different form of the view. Says that pseudo opens in this direction. Because it opens above TC, above the fermion, you cannot do it. But in the electron case, it is below that. So we don't have a complete experimental evidence that the whole took place. brings that to pick up that brings this point, like this point. Yeah, combining substantial evidences.
Right. So yeah, this this remind me of this kind of view for a long time.
Yeah.
Since Anderson's proposed this argument. Okay. This dark fermion that you mentioned is really not possible to be observed, or maybe it could be observed.
Dark fermion itself.
That's right.
Effect of dark fermion can be observed in as a
I know, but direct evidence.
Yeah.
Like dark matter. Okay. Any further question or remark? Yes.
One of the outputs data can show that they are featured from the how do they make it? So in one of the outputs data you show, so we observe something about
yeah.
how do they observe it?
This essentially division by perimeter function, but it's more. It is so exactly division. Wow. Elaborate. That's all. So gap is at least here. It is here. We don't know it. Fortunately, they don't show this one. I think that how it is slowly decaying. So gap should be around here.
Due to the constraint, so we could still ask questions to Professor Fujimori during the coffee break. So let's thank Professor Fujimori again for the wonderful. I will have a coffee break until 3:45. Yeah.
You did open your some sort of air density way.
然后我的想法是这样，就是拍了你的单，就看后一个单，就是想要拍了你的单，这个对的。那我可以解释，反正你可以让自己比较。
I read that one.
Okay, so you more.
Yes, expert coding.
下午的时候，我在玩的时候太悲了。
就直接把当成跟滴滴描述的，你把这里到然后这边这里没有生活到我的比较少。对，如果但是最多把时间单直接把时间那个这是最苦。这是也听到了，这边的话，听到你不满意的话，不会直接就说到，会比你用你挺放的。
我这个说是明晚的，概念是没有的，不一定是安完的，然后是第一个把才是这样。论文这个，好，你
有这个想法，
然后在做
第八节。可以了，但是我说他特别喜欢，太喜欢了。
要打我们有些同学谁也发，这方面也要去试，因为你还是这个方面哦，这个我们
太可以了，咱们这里比较熟悉。快，我可能了解。那我就也是有些节奏。这个路，
真想选大家看。
哇，你们真的哦，为什么？
这个记录留下来，就是说我这个未来应该有，然后谁会接下来他们因为其实在想，需要嘛？是应该比较交流，没错，还有一些哦，这个对这个。还有是包括水内场，
然后说的是把它拿去玩，
电毛区有这个，再深入。我之前也有参加了3年，
但是其实两方面啊，就是两个。
就心理也是来给。3分钟。因为我不知道他一会儿来。好的。
这量是差不多。理论上来讲，它一样的方法，但是其实如果是如果你可以裁成龙，它是为了这个第一第一个。我不知道，也许是他们当过有问题的时候，以前我六位现在他配备声称他是会宣称 PPT 它是做上
Okay, so let's resume our second handout session.
That's TFT end-of session, TMFT end-of session from morning's talk by Professor Ali. So yeah, for those of you who have practice, so yeah, please start. If you just introduce yourself.
Yeah. Hello, good afternoon. My name is Numan Khan. I am a PhD student of professor from CCU University. And in the morning, Professor Lee explained the physics behind the formalism behind the DMFT. And here we will start the hands-on session for the DMFT solution of metal and mode insulator and metal to insulator transitions. So first of all, we need to start some instrument in your computer. First, if you don't have Git, you need to install it first. So for installing it, you need to for Ubuntu Linux system, you need to write this command in your terminal to install Git. So first of all, every person here, you need to install this. So to have get install Git for Linux and for Mac system.
Microphones.
For Mac system, you need this command to install the Git. So I hope if you have, then we move to this. Then in your terminal, you can write this Git clone and this website to get all the files on which we will work. For the next, you can also go to the website directly and by downloading the all files from this option code. So after that, you need to have PIP3 install NumPy, SciencePy, Java, and before that, if you don't have PIP3, you first need to install this PIP code by using sudo apt install python 3 PIP. Or for Mac system, you can use this command. After that, you need to install Jupyter Notebook, and for Mac, you can use this command and Ubuntu or Linux operating system, you can use this command. Or if you don't want, if you have already this, you can also use VS Code instead of Jupyter Notebook. So please go for this and have all the files in your laptop. There would be 3 files, for one for metal and other one for insulator and one for metal to insulator transition. So you can directly download from the link, or you can use Git to copy all the files. This one is underscore DMF underscore.
So this or only use some.
If you have Git command, you can use this on your yes. If you don't have Git command, you can go to Google to this website and this option for
I wrote going to use so
then you will need to have this PIP3 styles. If you have PIP3 already, then you can install, otherwise first you have to install PIP. Okay. Using this. Yes. Yes. So
we're waiting for the participants to install this kit.
Yeah.
Maybe I can advise them.
Yes.
So, yeah. Does anyone don't know how to use GitHub? No. Okay. Yeah, I guess in general, if you have any question, you should just ask.
Okay. So we have 3 files, the MFT metal solution, which I will present here, and the other 2 solutions you have to do, and which are DMFT. So the DMFT mode insulator solution and DMT metal to mode insulator transition, and these are this one you need to find. This one metal. Okay, for metal insulated transition, we have Hubbard model, Hubbard model. These 3 diagrams are already explained by in the session. First, we need to have initial hybridization and the energy level. from that we will calculate the hybridization parameter, and then we solve for the green functions and for the self energy. And we will see that if the hybridization parameter converges, then we will stop. Otherwise, we have to again use for new hybridization and energy level, and we will iterate over until these are converged. And this graph shows the metal to insulator transition, and when the Coulomb interaction is increasing, the metal behavior goes to the insulator. And from this, we can see that if Coulomb interaction is increasing, the metal behavior is towards insulator. And you will see it here at the end. And I hope you have opened the code. And the first here, these are the all packages we are using to solve our calculations. And this one, okay. This code actually for semicircular green functions for semicircular density of states, and we use this formula to calculate the semicircular density of states for the green functions. And this one is written here in the code, and we get and this seems is the integration function for calculation of this green function. Okay, next we have a green function for the impurity model, and we use first we need to calculate this hybridization parameter, which includes the hybridization strength and the energy level of the bar. And after calculating this, we need to put this value in the last equation to get the green function for the Anderson impurity model. Okay, next we need to find the frequency dependent green function by the Anderson model, and we use this relation to calculate the for the real frequency green function for the frequency of the Anderson impurity model.
WS is omega.
Yeah.
Which EP and CP?
EV?
Input from EP and EP.
EV. EV is the energy levels of the both sides, and ED is the energy level. And I have also mentioned your code slides, which you are seeing the code. Okay, next here is the cost function for the context of the fitting, and we use this function for the convergence checking of this is the green function for best field, and this is for the Anderson impurity model, and then they should converge for and the cost function should be have minimized values so they can converge. Okay, next we have first we have the parameters. The temperature we are using is 0.005, and hoping parameter we are using 0.5, and chemical potential to 0.0, and number of bath levels here we are using 3, and for maximum max bar of frequency to fit we are using 100, and the mixing parameter used in iterative algorithm we are using 0.5, and the maximum iteration we use 500 iterations, and the number of max bar of frequency points are equal to number of frequency to fit. And this command generates the max bar of frequencies and to compute the initial green function. Here this part of the code use the exact diagonalization and initialization, and this part calculates the total number of spin and orbitals, and that prints out and constructs a list of fermion operators and total number of orbitals, and this part of the code we used for bath fitting parameter and initialization, and we are using Coulomb interaction in metal solution 1.5. Okay, now the iteration counter starts from here is equal to 0 and initialization difference variable iterative loop to converge on parameters. And this part of the code tells us about the fitting process of B and EB. And here the process starts like this. And after this, we have ED part, and this part will solve the impurity side, and solving the impurity Hamiltonian, we need to use this part of the code. And after computing Max-Bara-Green's function, we need to update the green function and the new green function, and we need to check the difference check convergence for this, which I already told. And this is the mixing solution for iteration +1. And then we have to calculate real frequency quantities, and this is the broadening factor. And then at the end, we have Max-Bara self energy. And we need to Max-Bara frequency impurity green function and Max-Bara frequency self energy. And then we have the quasi-particle weight estimate for Max-Bara self energy and real frequency lattice green function. Okay, now you will start to run this file, and for the metal greens function, where self energy U is equal to 1.5. After running this, you will get 4 graphs which are explained in the morning session. And after running this file, you need to run this file where we use the Coulomb interaction 4.0. And at the end, you need to run this file metal to insulator first order transition at temperature 0.005. And the last one is optional. If we have time, we will do it here. If we don't have time, you can do it by yourself. It is the UT metal to insulator phase diagram, which I get like this. So this is the temperature, and this is the Coulomb interaction. As we see that as we increase the Coulomb interaction, the metal transit to insulator phase. So, and this is the temperature. We have to run files on different temperatures. For example, I used 4 temperatures here to run the file and calculated the upper critical point and lower critical point, and then draw a graph between them. So we have used the temperature 0.005, 0.01, and 0.015, and 0.02. And after running these files on different temperatures, you will get that data, and from data you should plot this graph.
Yeah, let me just show the process.
In PS4 are Jupyter notebooks, which I either run. So for running, you need to click on the first and then you need to enter shift, enter.
Is it possible to upload also so we can, I don't know whether it will be too big.
Okay, next we will combine this shift enter, shift enter, shift enter. Files are running. Here we can see that different state is comparison in these iterations.
Upload the slides now.
Okay.
Actually, don't go.
Yeah.
Yes, if possible. The main problem is it's difficult to solve. So we have done tutorials like this in the past. Set up the server, where you can connect to it and run both on the server. Yeah, that should. It depends on yes. Yes.
对，就相关的。
哦，其实我这就也是有看见过，有用到。
对这个来说，所以昨天听到你讲那个数学这个，我蛮有感。有感吗？对。好，这大概是。
现在没有怕的，
对，就是头脑还是
第一个不是头脑，一直都有一个，第二个应该是跟那个是不一样的，
所以他们像我们
我们大概两个。
好像有一个有这种的，知道别人都知道，但是每个人都会上来，送，哇，这个大的，要这个时候有点大，
Okay, so we have a graph. Between spectral function and the analysis, and we see a short peak at the Fermi energy, which metal solution because at the Fermi energy we have a quasi-particle excitation.
Very cool. Do you guys reproduce this now? Leave your computer, let me see. It takes no time, right? How long do you need to get this? A few seconds. Yeah. You have a problem? All right. Oh, have you used that?
Next, we have the graph, imaginary part of the function, and we see that at zero, you can see short of the imaginary function. It's also chosen. And next, we have the graph, which is imaginary self-management and fluency, and for you, and we also see sharply.
我们第二题是什么？我们就套上来的。哇！
And this the last graph of this calculation, which is the imaginary self-energy or max ద్వారా frequency and frequency. Okay, next we have mod solution from DMT. We'll open this code.
What's this?
This is mod solution. And
Vector function.
yes, vector function. We have a gap.
The mod gap.
Yeah. So what did you change? What did you change?
U. Or delta. U.
There, it can find.
This one. 3.5. 3.5. So why are there two double peaks on either side? You don't know why?
Because we use Z normalization with a small number of bets. So yeah,
Finite size.
very small. Now important. So
Maybe the finite size.
yeah, finite size.
Okay. Great.
So it shows the output behavior as we show into solution. In this graph, self-engaged divergence at 0.
Right, yeah. You can write Python program, rubbing inside the top, like state exchange, and making it together. You don't actually need to post it. Excellent. Yeah. Yes, it's very big.
Okay, so what is this? I see. So it's imaginary part of the self-energy will diverge the minus infinity, which indicates what? Yes, open yes. If you have some difficulties getting this, you could raise your hand and
Organize we are taking this and as we are increasing you can
Yes, for all the systems. Yes, we use the previous say initial convert to best.
Is there an easy way to turn off numbers report? So into critical before that's part of the oh yeah, okay, yes. Yeah,
So actually, so how to
做出快把那个操作图画打开。对，就是这个问题的话，就会这个点就会拿到差一点这个所以呢，也在这个大家在。在这个不知道不是每次的话是走了。那么如果的话，看好的话，不要了解到，我知道这是这样子啊，所以就这个有大家的一个如果是其他的是的话，是的，这样子。今年我觉得，包括其他的，这个我们是这个我假设有人是，但是有人没有人开始，对，然后这个另外就是这个自然的。
得到新的人员会回来给你玩，那你提供给后，对，我们可能这个东西是，因为这边是个，然后从这个句子或者是他那个我知道到这个是因为就开始就这些，对，还是这个上面就可以做对打猎，对那。这个是，这个事情，好，最开始还是33，目前哇，能烧什么？哦，那个你们有，我。是现在我带的是这样的，就是因为还是不是对，是要习惯，这样然后别人其实有传出来说，这个我这里就去发现就有但是按照这款词典，但是我那个是有所以你们学的有这个对，不是。做学
对，这个普通的人更少些，所以这个是你就讲，这个是对对，结果这个叫上对，老师你想做职业培训，那个也是完全是孩子的机会，也是非常的复习。市面上学的比较广泛的价值。真好的，才不是变感。或者是应该是专门的我有配过去给他们。对，但是会哦，这个哦，差别。那个过程真的对，因为大家去结婚比较会对，那我们不需要用到我们的我们可以哦，你可以开这个，哦，像这个非常哦，这样子还有地方，我等下去，这个我也需要。只有人知道的，我们把这个然后比较老板是 那个是只是打到自己的如果我是一个大的对，是我的后一样，就是可以得到的，它就是。就是像自己的书，就是这个嘛，对，在这些方面3年吧，对，2年后的1年，哦，这是个例子哦，会少这个嘛，只要对吧？因为如果是了解小，然后人物质，我们还是可以讲这个大众的少的这个地方。但是很多时候很多问题是说上台面很大，做的是跟带的是多但是我们用的话，或者是说小学吧，所以我就是老师都是要自拉上，然后以前那个还是要那个把它们知道，这个过程，都很难听这样的啊，写作那个地方，哦，你们的赛还是真的是不要太少。可以维持。那个字少，它是太粗。哦，马改，马改，它是一个聪明马改，对。手的，然后才能马上。所以你看他们面对他们那边不知道资源还是小一点。哦，这个怎么有可以
Okay, so let's thank the instructor for this wonderful tutorial, and we end this tutorial. And Jiaming will say a few words at the end of the summer school.
Okay, let me say something and close this summer school. Everybody can go home. So yeah, so I don't know what do you think, but I enjoy very much. I learned a lot in summer school, and I think this is really a good idea that we have kind of joined the workshop. So I would consider this as a successful workshop. So yeah, hopefully we'll have some new idea, and hopefully we will be this kind of joint workshop in the future. Okay, so if you have any suggestion, any complaint, you are very welcome to send an email to us. Yeah, it will help us to improve the event. All right. So then thanks everyone's join,
So we also want to thank the secretaries and our founders that have arranging this lunch box and reserving and drink and so on. Okay. Thank you. So see you around and let's feedback. See you.